Hello everyone. In this section, we will try to understand how do we come up with the width and height of core and die. Okay, so in the physical design overview flow, this was the first step to define the width and height of core and the die. That was the first step of the physical design flow. So in this sections, let us try to understand how do we come up with the values of W and H. Okay. So what we'll do is we'll start with the basic netlist, and the basic netlist that we'll be using is, let's say, two flip-flops, the launch flop and the capture flop, and you have a simple combinational logic in between them. Okay, so our netlist will be considering only of this one for now. Let's say if we are trying to get the width and height of core and die, so let's take this as an example to identify the width and height of the core and die, and then this can be extrapolated to millions of gates. Okay, so this is the netlist, basic netlist that we have, and some connectivity. So A1 and O1 are your AND gates, OR gates, and they are basically they fall under the class of standard cells. And the flip-flop 1 and flip-flop 2, they fall under the class of registers or flip-flops. Okay, so this is the netlist. A netlist basically defines the connectivity between all the components. Let's move on. So in this case, we are mostly while defining the dimensions of the chip, we are mostly dependent on the dimensions of the logic gates which is sitting over here. So basically we are dependent on the logic gates and dimension of the AND gate and the OR gate and this particular flip-flops. So let's try to give a proper length and breadth to this particular gates, and this is how it will look like. So you have your launch flop with a square shape or a rectangle shape. You have your AND gate with again a rectangle shape. You have the OR gate and you have the flip-flop. Okay, next step, what we are mostly interested is to find out the dimensions of your core and die. So in that case, we are mostly interested in the dimensions of the standard cells and not the wires as of now. The wires will still play an important role in the further steps, but in this case where we want to identify the dimensions of the chip, we are mostly interested in the dimensions of the standard cells. So let's try to give a rough dimensions to all of them. Let's say the standard cells are given a dimension of 1 unit by 1 unit. This is 1 unit and this is 1 unit. So the area of this particular standard cells, all of them, will be 1 square unit. So this is 1 square unit, this is 1 square unit. And also let us assume the same area for the flip-flops as well. Okay, so the area of the flip-flop will be 1 square unit. Okay, so now what we'll do is, with the help of this netlist, with the help of these dimensions, we'll try to identify the area which is occupied on the silicon wafer. Okay, so but before that, let's try to place we'll remove the wires, and let's try to club all of them in a single plate. So for example, we'll bring the flops over here, we'll bring the AND gates and the OR gates all over here. And now if you try to calculate the total area or total length and width, so the length will be 2 square units, the width will be 2 square units, and the overall area is 4 square units. Sorry, the length will be 2 units, the breadth will be 2 units, and the area will be 2 into 2, which is 4 square unit. Okay, so so now we have a rough dimension, or we have a rough calculation of the area of the netlist. So this is the area of the netlist, area occupied by the netlist, minimum area that will be occupied by the netlist wherever it is placed. Okay, let's look into the core and die of a section of a chip. So for example, this is your silicon wafer on which you implement all of your logic. This section is the section which is this one section is referred to as your die. Okay, and inside the die you have this core. So this is the core section where you place the fundamental logic, where you actually place this logic, and this is the die section. Basically this encapsulates your core. Okay, and this is the piece of the area on which your circuit is built. So your circuit will not exceed this area. That's what the point is. And we imprint this particular die multiple times on the silicon wafer to increase its throughput. Okay, so those are all the fabrication concepts. Let's come back to defining the width and height of core and die. So let's try to place this particular logic inside the core and see what happens. So if you see, this particular netlist, which was of 4 square units, occupies the complete area inside the core. So what does that mean? You have actually utilized your core 100%. Okay, so if there was some area left out, then it would not have been 100%, it would have been some other percent. But in this case, your complete logic, your netlist is completely occupying the core area, and that's why we call it as 100% utilization. and your utilization factor. So with the help of the 100% utilization, we come up with a term which is utilization factor, and the definition for utilization factor is the area occupied by the net list, which is 4 square unit, divided by total area of the core. So area occupied by the net list is this particular net list, and total area of the core is the area of this particular core. So if we put in the dimensions over here, the area occupied by the net list is 4 into 1 square unit. Okay, and the utilization and the total area of the core is 2 into 2 square units, so which is 4 square unit by 4 square unit, and the utilization factor comes to 1. So when we say the utilization factor is 1, which means your core is completely occupied, and if there are some extra cells that we need to add in the core, that is not allowed, or that is not possible, because there is no space left. So in a practical scenario, we ideally have some amount of, we don't go for 100% utilization, we go for a 50-60% utilization, and the utilization factor will be 0.5 or 0.6. But for the proof of concept, we are trying to explain that 100% utilization means your core is completely utilized and there is no space to add any extra logic. Okay, with this particular, let's try to explain one more concept with the same example. You have this aspect ratio, you have the concept of aspect ratio. So when you say the term aspect ratio, or the definition of aspect ratio is height by width. So in this case, the height of this particular logic is of this particular core is 2 unit, the width is 2 unit, so the aspect ratio comes to be 1. So whenever the aspect ratio is 1, it signifies that the chip is a square shaped. Whenever your aspect ratio is some 0.5 or something, or some other number other than 1, it signifies it signifies that your chip is basically a rectangle shape. Okay, so what we'll do is we'll take some more examples. Let's say we'll take another example, and we'll keep these definitions at the right side. The utilization factor is area occupied by the net list divided by total area of the core. Okay, and the aspect ratio is height by width. Okay, with that in mind, let's take another example. So we have the same net list with 2 unit as the length and 2 unit as the height, and let's say now the area, now the core and the die look something like this. So this is your core, and let's see the dimensions of the core. So the core is 2 unit height, the height of the core is 2 unit, the width of the core is 4 unit. Okay, in this case, and now we place this particular logic inside this. So if you place this particular logic inside this and go by the definition of utilization factor, in this case the numbers will look something like this. So utilization factor will be 2 square, the area of the net list, which is 2 unit cross 2 unit, and the total area divided by total area of the core, which is 4 cross 2. So this is 4 cross 2. So utilization factor will come to across 4 square unit by 8 square unit. So utilization factor is 0.5. So 0.5 signifies a rectangle shape, or anything other than 1 represents a rectangle shape, or anything other than 1 represents that you have the core is 50% utilized, and the remaining, there is some extra amount of area that can be used to place some additional cells. For example, you need some optimization that has to be done. You can use this area to add some buffers or something. Okay, and similarly, if we try to calculate the aspect ratio for this particular dimension, it will be 2 by 4. So this is 2 divided by 4, which is again 0.5. So you must have heard these terms aspect ratio and utilization factor while building a chip or while doing a floor planning. So this is what it actually means, and this is how it comes from. So what we'll do is, since we'll take some more examples, let us take an example of a square chip. So since I'm already running out of time, let's try to take an example of a bigger chip. We'll try to place this logic inside this and calculate the utilization factor and the aspect ratio. Let's try to do all this in the next video. Thank you. Hello everyone, let's continue our discussion on defining the width and height of core and die. So we looked into how do we come up with a utilization factor and the aspect ratio terms and some examples for it. So let's take another example. For example, we have this square shaped chip, okay, and the dimensions of this particular chip are something like this. You have the core height as 4 unit, you have the core width as 4 unit, and now let us try to calculate the utilization factor and aspect ratio. Okay, so what we'll do, we'll place our existing circuit onto this particular core, and this is how it looks like. Let's say we place it somewhere over here. Okay, now in order to calculate the utilization factor, you need the area occupied by the net list which is nothing but 2 into 2 units, which is 4 square units. Okay, this is the area occupied by the netlist and the total area of the core. You have the height as 4 unit, you have the width as 4 unit, so total area of the core is 4 cross 4, which is again 16 square unit. So 4 square unit by 16 square unit, you have it as 0.25. So it says that out of the complete chip area, 25% of your chip has been utilized. Okay, and the remaining 75% is available for you for optimization and for all other things. So 25% of the core area has been utilized by the initial netlist, which is completely connected by wires, or which will be completely connected by ideal wires, which don't have any shape or size. And you have 75% of the chip area available for you, where you can place the additional cells, where you can which can be used for routing. Also for routing, there will be some more layers of routing. So basically when we do a routing, this is on one layer. On the top of this there will be one more layer, and where you will be doing the routing and all those things. So we'll talk about that in some other videos. So you have the 75% area available for cells only, for placement of the cells only. Okay, and now let us calculate the aspect ratio. So when we try to calculate the aspect ratio, it's height by width, sorry, it's height by width. So height is 4 unit, width is 4 unit, and you have your aspect ratio as 1. As talked about the aspect ratio in the previous videos, where wherever you see an aspect ratio of 1, it is supposed to be a square chip. Okay, so this is how you come up with the width and height of core and die. The next point in the next step in this particular physical design flow, or in the flow of floor planning, is to define the locations of pre-placed cells. So before we go into defining the locations of pre-placed cells, let us try to give you a brief overview of what does pre-placed cells actually mean. Okay, so again we'll take another example. Let's take a combinational logic. So the assumption is this combinational logic does some amount of function. Okay, it does some function. Maybe it's a memory, or maybe it's a multiplier, or it's a mux, it's a complex mux, or it could be any clock divider, any complex clock divider, or so on. This basically, this combinational logic does some amount of job. Okay, and it does such a big task that the output of this combinational logic is a huge circuit. It's a circuit of, let's say, some 50k gates or some 100k gates. So it's a huge circuit. Okay, so there is a way that we did not implement this circuitry every time as a part of the main circuitry, but we can take this piece of the circuit out of the main circuit and then implement this separately. And even we can granularize this particular circuit itself. So if this was, let's say, 100k gates, we can divide this circuit in such a fashion that you can make it actually 50k gates and 50k gates. You can make two blocks of 50k gates. So it looks something like this. So for example, let's take this particular circuitry out, and this circuitry is a part of your main netlist. Okay, let's take this piece out of the main netlist and do few things on it, do few processing on it. So what we'll do, let's try to cut this circuit into two parts. Okay, so we'll cut this circuit into two parts. This is one of the parts, this is one of the sections of the circuit, this is one of the sections of the circuit. Now the idea is we'll separate both of them. When they are attached together, or when they are connected together, they perform some function, but right now we'll separate them out. Okay, something like this. So we have this cut 1, we have this cut 2, and we have this connectivity information. If you see, these are the connectivity information that you see. So A1 is connected to A5 in this fashion. We have all this information from the cut 1, we have all the information from cut 2. Let's try to separate this out as two different blocks. So now if you look into A1 is connected to A5. So A1, the output of A1 goes to A5, the output of A4 goes to A6, the output of A4 goes to A6. Okay, these are two different blocks. Let's try to put it in that way. These are two different blocks, and this block will be implemented separately, and this block will be implemented separately. Let's see how. So we take these two separate blocks, two blocks independently, and give and extend the IO pins over here. So when we say, so our input output pins, basically these are the input pins of this particular block. This is the only output pin of this particular block. So let's try to first extend those pins, and it will look something like this. Okay, so this box will have this is the input side of this box, This is the output side of this box. Okay, now let's try to detach these two blocks. Okay, we'll black box this box and try to detach them. So when we black box this particular box, this section of the circuitry, or this section of the circuitry, is invisible for the one who is looking into top, who is looking into the main netlist. Okay, so now this section is invisible to the top netlist, to the netlist that we have implemented. This section of the netlist is invisible to the top netlist, and we'll separate them out. We'll separate this two boxes out, something like this. So this four outputs of this particular block will behave as four output ports. These four ports for this particular block will behave as an input ports. Okay, and this block will be implemented separately, this block will be implemented separately. The advantage of doing this is, for example, this block or this piece of the circuit is being replicated multiple times on your chip, or in this particular thing is being used multiple times on a netlist to perform certain function. You need not implement this one multiple times. You can just black box them. You can give this particular block to some user, you can give this particular block to some user, and those two users will implement these blocks separately, and that will be implemented only once. And then these blocks can be connected in this fashion multiple times onto the netlist, and can be used whenever it is required. So you did not implement this multiple times, you just implement it once, and then it can be reused. So this is the concept of reused models, where we have these small modules, and that can be reused separately on the top level, on the top netlist. Okay, now for example, there are other IPs also available, readily available in the market. It's something like this. If you can have something like memory, you can have something like a clock gating cell, a complex clock gating cell, you can have something like comparator, you can have something like mux. So all of them can be implemented once, and can be instantiated multiple times onto a netlist. So this need not be implemented multiple times, because this is a part of your top level netlist. They perform some functions, they receive some input pins, they receive some input signals, they deliver some output signals, but the functionality of this particular cell will be implemented only once. And that's what we call it as pre-placed cells, because these cells are being just placed once in the chip. That we have to define the locations or the arrangement of this particular cells, and this has to be done before the routing, before the actual placement and routing. So the placement of these cells on a top level chip will be fixed, and since they are placed before the actual placement and routing, they are referred to as pre-placed cells. Okay, so these cells are placed in such a fashion that the automated tool, whatever the placement and routing tool we have, that will not touch the locations of this particular cell. Once they are placed on once their locations are fixed onto a top level, on a floor plan, they are fixed, they are not touched, or they are not moved by any of the automated placement and routing tools. Okay, so what we'll do is, since we understand what the pre-placed cells are, we'll try to take few of the pre-placed cells, or few of the cells, let's say block A, block B, whatever we discussed in the top. We'll try to take that cells and place it on a chip in such a fashion that their locations are not moved. And once they are placed, they are fixed in that locations, and the further steps will not touch those locations. Okay, so let's try to do that small part in the next video. Thank you. Hello everyone, let's continue our discussion on pre-placed cells. So in the last video we talked about pre-placed cells, where these cells are nothing but macros or IPs, which is a piece of a complex logic, and that is being reused multiple times. So these were, for example, let us consider these are the pre-placed cells that we have. Let's say block A, block B, and block C are, let's say, memories. So we implement memories once, and then they are being reused multiple times on the circuit. And also these memories can part of any devices or of any hardware. So we need not implement it every time whenever it is going to each and every hardware. We implement it once and then use it multiple times. Okay, so how do we define the locations of pre-placed cells? So for example, we have a design background which says that this side of the chip will have all the input pins, and this side of the chip will have all the output pins. And also from the design summary, we come to know that this particular blocks are most of them are communicating with the input pins. So we come up with a design scenario where we place all these blocks close to the input side, something like this. You take the block, place it to the input side, you take this block B, place it to the close to input side, and you take this block C, and it is also placed close to the input side. So these pre-placed cells, has been placed in this area depending on the design scenario or depending on the design background. So the locations of these pre-placed cells are never touched while we go in the design cycle. So the pre-placed cells has to be placed in such a fashion. Basically, once they are placed over here, the locations can't be moved from in the complete design cycle. So the locations of these pre-placed cells has to be very well defined. Okay, so that's how we come up with the locations of pre-placed cells. Next, there is one more thing that we need to do with the pre-placed cells, is that we have to surround them with decoupling capacitors. So let me give you a brief idea of what this decoupling capacitance is and why do we need it. Now, why do we need this? Okay, let us consider this piece of circuit is a part of any of the block A, block B, block C that we saw just now. Okay, so this is in our example, this is the main circuitry, but for example, let's consider this is a part of the block A, block B, or block C. Okay, whenever this particular circuit switches, for example, let's say if you take this particular AND gate, and when it switches, when the output of the AND gate switches from logic 0 to logic 1, there is an amount of current demand that it needs. Basically what happens, there is small capacitance which is sitting over here, and whenever there is a transition from 0 to 1, this capacitance has to completely charge to represent logic 1, and the amount of charge to this particular capacitance will be sent from the supply voltage, or will be sent from this particular supply voltage. So it's the responsibility of this supply voltage to supply the necessary amount of current to this logic and to all other logic whenever it is switching from logic 1 to logic 0. Sorry, whenever it is switching from logic 0 to logic 1. Also, whenever any piece of the circuit is switching from logic 1 to logic 0, it is the responsibility of the VSS to take that amount of charge. So basically when we say logic 1 to logic 0, the capacitances which are present in this circuitry, that will get discharged, and those discharge current should be handled very well by this power supply ground line. Okay, so that's the intent. But now in reality, when you see, if you see this is particular power supply source, and when this particular power supply flows from piece of wire to this particular circuit, there is a drop in the wire. And why there is a drop? Because these wires are nothing but physical wires which has got some physical dimensions, and anything that has got a physical dimension will have some resistance, inductance, and capacitances that is associated with it. And since we have this resistance, for example, for now let's consider we have resistance and inductance, and this resistance and inductance are repeated multiple times on this particular piece of wire, and they are also present over here as well. So whenever this supply tries to move from or tries to flow from this point till this point through this particular path, there are multiple voltage drops happening over here. So for example, let's say VDD, let's say 1 volts, which is supposed to be 1 volts, when it flows through this particular wire, there is a drop over here, and that drop is referred to as, let's say we call it as VDD dash. So if this is 1 volt, it's always not possible that you see this VDD dash as 1 volts, but it could be less than 1 volts, let's say 0.8 or 0.7 volts. Okay, now the 0.7 volts should, for example, now let's say if this is 0.7 volts, the output, if there is a charging happening from logic 0 to logic 1, can't go more than 0.7 volts, because that's the amount of supply which is available over here. Now 0.7 volts for this particular logic, for this particular transition to be detected as logic 1, the 0.7 volts that we see over here, that should be within the noise margin range. Okay, the noise margin diagram looks something like this. So you have this bumps, you have this particular bumps where anything which any voltage which lies between VOL and VIL is called as logic 0. Any voltage which lies between VIL and VIH are called as undefined region. So when we say undefined region, basically the logic can either move from logic 1 to logic 0, or basically from this area to logic 1, or from this area to logic 0. So any supply voltage which is lying over here can go to either area. That's why it's called as undefined region. Okay, so whenever this is a scenario, it's a danger case. And whenever a logic lies between VIH and VOH, it is always it is treated as 1 volts, or it is treated as logic 1. So if the 0.7 volts that we just discussed in the previous, for example, if this VDD dash lies in this particular noise margin area, we are safe. But if the voltage drop over here is too huge, let's say it's not 0.7 volts but 0.5 volts, and if 0.5 volts lies somewhere in this area, we are in an unsafe zone. That might lead to either to move from logic 0, from this area to logic 0, or from this area to logic 1. So it's basically an undefined area. It's a gray area for us. So we can't guarantee that we expect a logic 1, but we can't guarantee whether we'll be getting a logic 1 or not. Okay, so that's the problem of having a physical distance, having a large physical distance from the main power supply to this particular piece of circuit. Okay, so one thing what we can do is we can solve this problem with the help of decoupling capacitors. So decoupling capacitors are something you can consider. The decoupling capacitors are huge bunch. It's a huge capacitor which is completely filled with charge, and this is filled with charge. Let's say it is the equivalent voltage of the across the decoupling capacitor is similar to what you have across the power supply. Okay, let's say if this was 1 volt, this is being charged till 1 volts. Whenever this particular piece of circuit switches, it gets its power supply, or it gets its current from the decoupling capacitor. So basically, when we say decoupling capacitor, this capacitor decouples this particular circuit from the main supply. Okay, so whenever there is a switching activity happening, decoupling capacitor will send the current to this charge, and since decoupling capacitor are placed close to this particular block physically, there is hardly any voltage drop from this point till this point. So if this is VDD, this will be VDD, and the amount of current that this particular circuit needs, that is supplied by the decoupling capacitor. That's the importance of decoupling capacitor. Okay, so we have covered the concept of decoupling capacitor and the noise margin in a separate section of videos called as crosstalk. You might want to have a look into those videos. Every detail has been explained over there, along with some equations which actually justifies what is the amount of current, IDD, what should be the value of IDD, and what is this peak current, what is the switching current. All those things has been very well described in the crosstalk videos. You might want to have a look into those videos. Okay, so this is the case where you use the decoupling capacitor to charge this complete circuit. Now whenever there is a switching activity, this decoupling capacitor or this capacitor loses some amount of charge to the circuit. Okay, and whenever there is no switching activity happening, the decoupling capacitor spends its time to replenish its own charge. Basically it gets charged because this is a huge amount of capacitor. It already has some loaded charge in it. Okay, and whenever there is some amount of charge gets discharged in this area, it again gets charged from its main power supply. Okay, so this basically, the name itself suggests that it is decoupled from the main circuit. So in the chip it will look something like this. Let's say you have some blocks of decoupling capacitor, so you place it over here, you place some decoupling capacitance over here, you place something over here, and you place a decap over here. So in this way, the complete blocks, the complete pre-placed cells are being now ensured that they get their supplies from the decoupling capacitor. So this block will now behave as it should be, and there will be no switching activity that will get missed, and there will be no problems of crosstalk over here. Or basically there will be no problems where the logic 1 is not rated as logic 1, because we have this decaps which is placed across the memories, or let's say these blocks, that will supply the required amount of charge to these blocks whenever they are switching. Okay, so once we're done with this, we have taken care of the local communication. So any communication happening over here, we have taken care of that. But what about the global communication? So let's try to talk about more about global communication with the help of the concept of power planning. So let's try to do all this in the next video. Thank you. Hello everyone, let's continue our discussion on power planning. So before we enter into the step of power planning, let me try to introduce you to a problem first. So we had seen this initial problem where this particular circuitry was demanding current at the same time. Basically each and every element of this particular circuitry was demanding current, and the decoupling capacitor was supposed to provide all the charge or all the current to any of the element present in this particular circuitry. Okay, let's take this particular circuitry and keep it as a black box. Let's say that was a macro. Let's say this was a macro. Okay, now the second problem statement is, if this particular macro is being repeated multiple times on the chip, then there will be current demand for each and every element of this particular macro. Let's see what I just said. Okay, for example, this was one of the macro, or this one of the block for which the problem was solved using decoupling capacitor. The problem of the current demand was solved using decoupling capacitor. Similarly, we have this particular macro being repeated 4 times. Okay, let's say this is your complete chip, and it has got these four macros, this macro being repeated multiple times, and there is some logic which is present at the boundaries also. Okay, now also assume that this is the driver, this is the load, and there is a signal that is being sent from driver to load, and the signal is basically logic 0 to logic 1. Okay, so what in this scenario, what we have to do is we have to make sure that this particular complete line maintains the same signal, so that the load receives the same shape of the signal. This is what we have to make sure. Okay, now let's see where the problem lies. So now let's try to connect all of them to the power supplies, something like this. You have this particular power supply, you have VDD, you have VSS. The VDD lines goes over here, it goes over here, and this blocks has been tapped to the VDD. This blocks has been tapped to VDD. Okay, and similarly you have the ground line which goes here, and all the block ground lines are tapped to ground. Okay, we see all of them, we see them in the for all the 4 blocks. Now assume that this particular line, assume that this particular line is a 16-bit bus. Okay, and before that, when we say that this particular line has been charged from logic 0 to logic 1, basically driver is sending a signal from logic 0 to logic 1. So this complete signal, this complete line has to retain this particular scenario, so as the load should receive the same signal. Now for this particular line to retain the same scenario, it should get the necessary supply from the power, because now in this region we don't have any decoupling capacitor that will take care of this particular scenario. So since we don't have any decoupling capacitor in this area, the power supply is the one who has to supply power to this complete line. And also it's not very feasible to put decoupling capacitor on all over the chip. So some sections, some critical blocks are being decoupled from the main supply using decoupling capacitor, but not for each and every element. We can't do that, it's not feasible. Okay, so over here if you see, this particular line has to be taken care by this power supply, and now this power supply is sitting a bit at a far distance from this particular line, so there is always a possibility of voltage drop. So what you see VDD over here, that might not be VDD on this line, but it might be something else. Let's try to see how. Let's try to see what will be the value of this particular, what can be the value of the VDD and the ground at this particular point. Okay, so let's assume that this is a 16-bit bus, and let's try to take the initial conditions of 16-bit bus. So let's say this is a 16-bit bus. This was the blue line that we talked about, and this is the initial state of the 16-bit bus. So when we say the logic, the each and every line is logic 1 or logic 0, this is what we mean. So when we say one particular line of the 16-bit bus is at logic 1, it says that that's a capacitor which is being charged to VDD. Again, there is a capacitor which is charged to VDD. Similarly for this line, whenever we see 1 1 1, these all 3 capacitors are charged to VDD. Wherever we see 0 0, these capacitors are discharged to ground. They're already discharged to ground. Now let's take a scenario where the 16-bit bus, we just saw the 16-bit bus, where this particular 16-bit bus is connected to an inverter. Let's say this particular inverter, let's say it is connected to an inverter. Okay, now what will happen, when you pass this particular logic to the inverter, the output of the inverter will be an inverted value of the input. What does that mean? All the capacitor which was charged to logic 1, they will all get discharged to logic 0 at the same time, and this particular capacitor which will all discharge to 0 will now all charge to logic 1. In that scenario, what can go wrong? Let's see that. So for example, let's say we will be taking a scenario where all the logic 1s, all the V's are switching from logic 1 to logic 0. Basically all the capacitances will are discharged from logic 1 to logic 0. And now since all of them happen at the same time, and we have a single ground line for the complete 16-bit bus. So since all of the capacitor will now discharge their charges at the same time, you see the ground which was supposed to be logic 0, there is a bump over here, and that's what basically is called as ground bounce. And if the size of this bump exceeds the noise margin level, it might enter into an undefined state, as we discussed in the previous lectures, and due to the undefined state, it can either go to logic 1 or logic 0. So things becomes a bit unpredictable over here. Okay, and since all of the capacitances which was charged to VDD are now discharging to ground at the same time, basically it's basically saying that this is one line and there are different taps, and all of the taps, all of the water taps are being opened at the same time. So during some point of time, at some point of time, you see that the water level at some area just increases, and this particular that. So water level is supposed to stay at this level, but due to the taps opened at the same time, there is an increase in the water level for some time, and then it will settle down, but that's a different story. Okay, this is basically, this phenomenon is called as ground bounce. And let's see what happens when you try to, when all these particular capacitances try to charge from logic 0 to logic 1. In that case, all these particular capacitances are demanding for supply from the main power supply at the same time. And since you have only single line for all these capacitances, you see there is a voltage drop because all of them are demanding current at the same time. It's basically there are multiple, let's say there are multiple buckets and a single tap. So single tap has to supply water to all the buckets, but it has got not enough supply to provide the buckets, and that's why you see a voltage drop. That's why you see a shortage of water. Okay, and this voltage drop, as long as it is within the noise margin level, we are good enough. But if it goes into an undefined region, the things becomes a bit unpredictable. So the phenomena that we saw was causing a lowering of the supply voltage. Either the VDD which was supposed to be VDD on these lines now goes somewhere less than VDD, and the VSS which was supposed to be 0 volts over here, it's somewhat at a higher voltage. Okay, so that's the problem that we see. And if you see the problems that we just discussed, those are coming due to one reason. The problem is the supply is being provided only from one point. If there had been multiple supplies, let's say there was a power supply over here, there was a power supply somewhere over here, if there were power supplies all over the places, then this problem would not have been happened, because now each and every line will look into its nearest power supply and get the supply from it. Okay, and that's exactly the solution for this particular problem. Let's see how. So let's say if you, in these cases, what is happening, the power is coming from the single source. Okay, it's coming only from one place. Instead, if the power had come from multiple places, that would have solved this problem. For example, something like this: instead of a single power supply, which we saw in the previous videos, we'll have multiple power supplies. We have VDD VSS lines. Okay, if you see, we have multiple VDD VSS lines, and now each of them, let's say if this particular block demands this has been taken care by the decoupling capacitor. If some logic which is sitting over here demands a current, it will take the current from the nearest power supply, or it will drop its current to the nearest ground. So it did not wait from a power supply which was sitting over here, but it can tap the power from its nearest power supply. So this is the reason that you see in the recent chips, there are multiple power supplies, there are multiple VDDs and VSS ports. There are multiple pins for VDD and VSS ports. Okay, this is exactly the reason for that. And similarly, let's say there was a line which was sitting from this, there was a line which was going from this point to this point. This particular line will take its current from the nearest power supply. Even the 16-bit bus will take the current, or take the charge from the nearest power supply, or dump its charge in the nearest ground line. So this is the logic. This is basically called as the mesh, and this is what exactly is the solution for our power. This is exactly the plan for our power. So this particular power planning, what we'll take one VSS line. Let's say this represents VSS, this represents VDD. So this will be all your VDDs placed in this fashion, and there will be again one more VDDs placed in a different direction, and they will be all connected. Okay, similarly we'll be doing the similar thing for ground as well. So you have these ground lines, you have the horizontal and vertical ground lines, and they are all tapped. Now any logic which is sitting over here will take its current from the nearest power supply, or will dump its current to the nearest ground. So this is basically the power planning of what we do. And in the recent VLSI chips, you might be seeing there are power meshes, there are lots of power meshes, and this is the reason for that. Okay, so we have discussed all of them in a separate section called as crosstalk videos. You might want to have a look into those videos. And what we'll do is, since I'm already running out of time, the next step is basically pin placement. It's a very simple step. So once we do the pin placement and the logical cell placement blockage, we are ready with our floor plan. Okay, so let's try to look into these two steps in the next video. Thank you. Hello everyone, let's continue our discussion on pin placement. So before looking into the concept of pin placement, let's take an example circuit. Okay, so we are planning to implement a small circuitry, a small handful of gates. This is one of the sections of that particular circuit. Okay, so for example, we have flip-flop 1, one of the sequential cells. We have flip-flop 2, and we have the input ports as D in 1 and the clock port as clock 1 and the output port as D out 1. Okay, similarly there is one more section. Let's say we have this particular section. It again has a flip-flop 1, flip-flop 2, but of a different color. And this flip-flop 1 is been driven by the input port D in 2 and the clock port clock 2, and the output port is basically D out 2. Okay, so this set of the circuit is driven by clock 1 port. This set of the circuit is being driven by clock 2 port. Okay, along with that we have some pre-placed cells as well. So we have done the placement of some IPs in the previous section. So these are those pre-placed cells. So we have this block A, okay, and the block has got some connectivity like this. So it receives its input from D in 1, from the D in 1 port. It receives its and second input from D in 2, okay, and the output goes to one of the inputs of the combinational gates. This is just a circuitry to explain the concept of the placement and routing. Okay, so we have this pre-placed cell which has got connectivity something like this, and we have another pre-placed cell, let's say block B, which receives its input from clock 1 and clock 2 and provides a clock output, and this is a clock output port. So currently now we have four input ports, which is D in 1, clock 1, D in 2 and clock 2, and we have three output ports, D out 1, D out 2 and clock out. Okay, so this is a sample circuitry for the design that we are planning to implement. Okay, and let's say there is one more section of that particular same design. So this section has got flip-flop 1, flip-flop 2, but of a different color. And this flip-flop 1 is being driven by D in 3, which is the input port, and this particular flip-flop 1 is again given clock 1. Okay, and this flip-flop 2 has got an output port which is D out 3, but the clock port for this particular flip-flop 2 is clock 2. So this kind of circuitry will be very good example to help understand the timing analysis for interclocks. So interclocks, by interclocks we means that the two particular two flip-flops are being driven by different clocks. So this is driven by clock 1, this is driven by clock 2. So that's basically the concept of interclock timing, and we'll be talking about that in the further videos. So this particular example will be helpful to understand those timing concepts. Okay, let's take one more section of the same circuitry. So we have this flip-flop 1, flip-flop 2, but of a different color. The input port is D in 4, the input clock port is clock 2. This flip-flop 1 is driven by clock 2, this flip-flop 2 is driven by clock 1, and we have the output port D out 4. So now we again have some set of input and output ports. We have D in 3, D in 4 as two new input ports. Clock 1 and clock 2 already had been defined in the previous slide, so we need not consider them over here. And we have two more output ports, which is D out 3 and D out 4. Okay, let's take one more pre-placed cell somewhere in the center. So we have this pre-placed cell block C, which gets its input from D in 3 and D in 4, and the output of this particular pre-placed cell goes to some combinational logic, let's say this particular NAND gate and this particular NAND gate. Okay, so now let's look into the complete design. We have taken this particular design. So it looks something like this. This is the first section of the design, this is the second section of the design, and this becomes your complete design. So let's make the connectivity first of all, a proper connectivity for this particular design. So for example, clock 1 is coming twice over here, clock 1 is coming over here and coming over here. So let's pull this and put it over here. So we'll take the clock 1 we'll take the clock 1 information from this clock 1 port. We'll take the clock 2 information from this clock 2 port, and similarly clock 2 and clock 1 will do the same thing. Okay, we just tie it up to the respective clock 2 port, and we tie this to the respective clock 1 port. Okay, so all these things, the netlist connectivity and everything, basically what goes to what, this connectivity is being defined in a separate tool. It's called in a separate language. It's called VHDL or Verilog language, and this particular connectivity of gates is refers to a netlist. So this is what a netlist means. It basically refers to the connectivity of different gates, the connectivity information between different gates. Okay, so now we have this set of input ports, D in 1, D in 2, D in 3, D in 4. We have two clock ports, clock 1, clock 2. We have 4 output data ports, which is DOUT1, DOUT2, DOUT3, and DOUT4, and we have one clock output port, which is clock out. So let's try to place all of them in the chip that we are trying to design. So we have this particular core and die, and there is an area between the core and die which is empty. Let's try to fill this up with the pin information. So generally the trend is we put all the input ports on the left hand side and all the output ports on the right hand side, but it might vary from designer to designer or from design to design. So some might prefer to put input ports at the top and output ports are at the bottom. Some might prefer to put input ports in the left and top and the output ports on the bottom and right. Okay, in this particular circuitry, we'll take an example where we put all the input ports on the left hand side and we put all the output ports on the right hand side. Okay, so let's do that. So we have this particular input ports D in 1, D in 4, clock 1, clock 2, D in 2, D in 3, and the output ports are placed over here. So there are two things that has to be observed over here. First of all, the ordering of the of the input ports are random. D in 1 comes first, then D in 4, then D in 2, then D in 3, and the ordering of the output ports are again random. So it's D out, D out 1, D out 3, D out 2, D out 4. And the reason is pretty simple. It's basically depends upon where we are planning to place the cells. Now for example, block A, if we refer to block A, it was been driven by D in 1 and D in 2. So we try to place it close to D in 1 and D in 2. Similarly, block B has got direct connectivity to clock out 2. So this could have been placed somewhere over here, but that would have required some additional decoupling capacitors. So we plan to place it over here, and we'll put some buffers for this particular block B to come out to clock out. Okay, and for example, there are again some cells which will be placed over here, which that refers to D in 2, and as a result of that, the D in 2 is being placed over here. So there are multiple reasons, and we have, and also what we have tried to do is, for example, we know that now we have a cell, we have a block which is placed over here. We have block A, block B, and block C. So no cells can be placed in this area, no flip-flops can be placed in this area. So we have made sure that all the input ports, which is D in 1, D in 4, D in 2, and D in 3 are out of this particular way, are out of this particular area. So basically, a complete knowledge of the design or of the functionality of the design is very important to understand the pin placement. So this basically creates an handshaking between the front end and the back end team. The front end team is the one who defines the netlist connectivity that we just talked in the previous slides, and the back end team has to decide the pin placement. So this is where the handshaking comes into picture. Okay, and the second thing to observe is the clock ports, which is clock 1, clock 2, and clock out has the clock ports are bigger in size compared to the data ports. Okay, and that the reason for this one is the clock is the port which is driving all the cells continuously. The clock 1 and clock 2 continuously send signal to the flip-flops, all the flip-flops in the design. So basically these are the one that drives the complete chip, or drive the flops in the complete chip. So we need the least resistance path for the clock 1 and clock 2, and bigger the size, lower is the resistance. Similarly for clock out and clock out over here as well. So we need the clock port, we need the clock signal to move out of the chip as fast as possible, because it is being driven continuously. So we need the least resistance path for the clocks, and that's what we have done. We have created bigger boxes for clock 1, clock 2, and clock out, so to make sure these are very least resistance path. So once we are done with the pin placement, the next step is to make sure none of the automated placement and routing tool doesn't place any cells in this particular area. This particular area should be blocked for the placement and routing tool. So that's what we do. We do a logical cell placement blockage. We block this particular area using some blockage, and this makes sure that the automated placement and routing tool doesn't places cells in this particular area, because this area is reserved for the pin locations. Okay, so finally when we have the logical cell placement blockage, our floor plan is ready for placement and routing step. Okay, so now we are done with the floor planning step, and the next step is to move into the placement and routing. So what we'll do is, since I'm already running out of time, and this is the end, this is the final lecture of this particular section, and from next section or the next video onwards, we'll move into the further concept of placement and routing. Okay, so let's try to begin placement and routing steps from the next videos. Thank you.
Hello everyone. So welcome to the second day of the workshop. So this workshop we will be covering the floor plan part of the workshop. So you have had the floor plan as well as planning done with the theory part. So this is a hands-on experience on floor plan. So as you can see on the screen right now, this is where we had ended last time. So we had done the synthesis flow, we had done with the design setup, and we did the flop count, flop ratio, the flop percentage, everything was done. So following synthesis, the next stage is floor plan. So in floor plan, basically we are setting the, as you learned in the first half of the session, we set the die area, the core area, we set the aspect ratio, utilization factor, we place the input output cells. Apart from that, we do power distribution network, that is the PG creation, and macro placement. Standard cells are not done placed in floor plan. Standard cells placement happens in placement stage. So so in OpenLane we actually have a lot of switches with which we can adjust the flow direction. So we will be as such to run a floor plan, all you need to do is just type RUN, just like synthesis, RUN underscore floor plan. But behind this, what all changes you need to do, all the switches, that's what our next focus will be before we run this run underscore floor plan. Okay, let it be here. So the switches which I was talking about, if you go to this location, that is OpenLane / configuration. See, I will do a PWD configuration. Inside it, there is a few TCL files as well as one README file. So if you open up this README file, you will see these variables which are required for each stage. So you can see these are the global variables, the design name, Verilog files, and then there is this synthesis stage, and beneath that you have a whole set of variables. You can see the library that is used for synthesis, the driving cell, the design rule constraints which are being set, that is the transition, max fan out, max cap load, so min and max library for the ST analysis. So these are the variables that you could set with the synthesis flow. So these variables are basically the switches which I was talking about. Similarly, just like in synthesis, we are done with synthesis. So in floor plan, we have this whole set of switches. So to begin with, this is the FP core util, which FP stands for floor plan core utilization. So core utilization, as you might have known by now, it is the total area of the netlist to the total area of the cell. So and you can just read through the description which says this is the core utilization percentage, and by default it is set to 50. Similarly, there is floor plan aspect ratio, which is the height to width of the core, and it is set to a default value as 1. Similarly, the core margin, which is the offset between your die boundary and the core boundary, which is set to a value of, which has a default value of 3.6 somewhere in the flow. Similarly, we have this IO horizontal metal, that is the, you can read description, IO vertical metal. So it's not necessary you need to set all of these. You can set any based on where you are in the flow. Like initially, see, PNR flow is basically an iterative flow. So at some point of time you would want some parameters to be active, and then at a later point of time you would want another set of parameters to be active. So you have, it's your decision, it's a designer's decision. Similarly, we have this 4 parameters which actually sets the power distribution network. PDN stands for power distribution network. and here is where we specify the decap cells which is to be used for floor plan, and this is all for floor plan, and this is the placement related variables switches, that is PL is for placement. Target density, which basically says that how close or how spread you want your cells to be. So a value of 1 means your design is very closely packed, and a value of 0 means it's like a lot of free spaces. So you would want a value. So in this case, by default, we have taken a value a little closer to 0, so that the design is spread. Because the reason why you would want a design initial to be spread is that when you begin the PNR flow, you would first do the congestion analysis. So post that, you slowly move towards as you move towards the design closure stage, the time you would want your timing constraints to be met. So it's firstly design is constrained with respect to congestion. So you want lesser congestion at initial period. So these are the switches that we need to set for floor planning as well as for placement. Now I told you about the switches. Now where are these switches set? So this README we had opened from OpenLane configuration folder. So as you can see, there are these many tickle files. So if you open this floorplan.tickle, you can see these parameters which they have been set to. So these are basically the default parameters which are set for floor plan stage in OpenLane. See this. So this is how you'd set it. Set, and this is environmental variable, and this is the variable name, the switch name. So this is setting all those values. So this all we have seen. Then there is something we didn't. That is the FPIO mode, which says that how you want your pin configurations to be around the core. So FP mode of 1 means you would have the pin positioned randomly but at equidistance, and for 0 the pin position won't be equidistant. So these are the system default settings. Now if you remember from our last OpenLane workshop video, I had mentioned you about two of the design specific files, config file. That is, right now if you see, I am in my PQR with to a design directory. If you do an ls-ltr, these two files, config.tickle and sky130.tickle. So sorry, yeah, this one. This was the one which I showed you now, which is the configuration directory. So the precedence is, the lowest priority is to the system default, that is these settings which we saw. After that, the next priority is for config.tickle, and post that the next priority is this ptk variant.tickle. So if you open the config.tickle file, let's see. So this is the design name. This is where the OpenLane is supposed to fetch its design files from, the .p file and .sgc. This is the clock period we have set. This is the clock net and the port. Here we have set core utilization as 65%. We set the IO vertical metal as layer 4 and horizontal metal as layer 3. So in the OpenLane flow, the vertical metal and the horizontal metal is one more than what you specify. So if you have specified vertical metal as 4, it will be 5, and for horizontal it will be 4. So let's see, this was our, what are the, so here core utilization is 50, vertical metal is 2 plus 1, that is 3, horizontal metal is 3 plus 1, that is 4. Now with these settings, so let's see what the run floor plan does. So we will do a run underscore floor plan. So it won't take much time. So these warnings which you see on the screen, so it need not be taken seriously, because this is basically saying that the source statement that is present on the left, it's an obsolete statement which is no longer required. So that is okay. So now open the floor plan run as successful. There was no error. That's why there is no success. It was successful. So just like how we did for synthesis, we will go to the runs folder. So today we will see the latest file that got generated. Now it's 10th September. We go to that folder. This minus LTR. We will do one thing. We will first check whether all the switches that we had set in the config.tcl, did it take precedence over these switches, system defaults. So for that, we will go to cd logs and we'll go to floor plan. So a set of logs will be generated post for floor plan. So we will open, I think it is an IO placer. IO placer will, because we had defined the metal layers for the IO, input output. So it will be inside this log file. If you go do a shift G, it will go to the end. Now this was what I was talking about. You see the vertical metal layer is 5 and the horizontal metal layer is 3. And let's check the config file which was present inside the design folder. Vertical metal is 4. That means the value it took is 4 plus 1, 5. Horizontal metal is 3. So in the design, the horizontal metal is 3 plus 1, 4. So this is correct. We have the config.tcl has, the design config.tcl has overridden the system defaults. And one more parameter we had set the core utilization as 65%. Let's see. So this is we are checking at the log level. And if you remember, I had mentioned you about the config.tcl file which is present inside the runs folder. So this is basically tells you all the configurations that are taken by the flow. So if we open this config.tcl, you can see which all parameters were accepted by were included in the current flow. So if you look for the aspect, core utilization here, yeah, this is an issue. We had set this is the default floor plan setting, and in it the core utilization was 50, and in the in the config.tcl core utilization is 65. But when we check the config.tcl that was used for the current run, it says that core utilization is 50. So it is an issue because the design config.tcl should override the system defaults. But there is one factor which we are not considering. If you remember, I told the highest priority is for this. So that core utilization should be 50, should be set to 50 inside this config.tcl. It should be. Yes. Can you see this line? This is the line which says the core utilization is 50. So the 50 of system default was overridden by the 65 of the config.tcl, and the 65 of config.tcl was overridden by 50 in this PDK specific config.tcl. So this was the priority I was talking about. So basically this has done you have completed the floor plan stage. but you would want to see how your floor plan looks like. So this is the run. So I'll clear the screen. I will go to CD results, CD results, floor plan. So you will see one def file here. So if you, def file is basically the design exchange format. So if you open this def file, you can see all this information. It says that this unit HD, this is the place site, it has been placed in this orientation at this location. So at the beginning of this def file, you can see something called a die area. So this basically is the area of your complete die. So you see two set of coordinates. 0, 0 is the first 0 is the lower left x value. Second 0 is the lower left y value. This value is the upper right x value. This is the upper right y value. So using this, you can basically calculate the area of your die. And what will be the unit? So this is set by this statement, units distance microns. So this is the database unit per micron, that is 1 micron equals 1000 database units. So these are database units. So if you divide these numbers by 1000, that will give you the area, the dimensions of the chip in micrometer. So that would be one of the assignments you would be getting. So this is the def file, but looking at the def file does not make any sense. So you won't know where what is placed. So to see the actual layout after floor plan, it is first done in Magic. So you do Magic -T for text file. So text file location I have here. This is the complete text file location. So I will break down this text file location. Just ignore, you just look from here. There is the Opalin working directory, PD case, Sky138, libs.text, Magic. This is the text file. With the Magic text file, we need the left file. So the left file which we will be taking here is the merge.left, if you remember from the last video. So the merge.left basically has combined both the cell left and the tech left. So that is actually present inside the temp folder, which is 2 level up. That means the temp folder is inside this folder. So we have to move 2 level up. So we move 1 level up, 2nd level up, we do a temp, we do a merge.left. So this is the left file. And finally, we do def read. And this is the def file. Now, since we already are in the location where def file is located, you need not put the entire path of the def file. And then you put an ampersand. So this will free up the this prompt when the Magic launches. So if you concentrate, when I do an enter, it will move to the next prompt. It won't occupy that CLI. Yeah, it has moved to next prompt. So Magic is opening. So now there are a few things that I would like to draw your attention to. When you maximize this window, you can see your layout is somewhat not centrally aligned. So to select, first of all, you need to select the layout, entire layout, and move it to the center of the display. So to select it, you press S on your keyboard. So you can see the entire layout getting highlighted, and then you press V. So that will fit this layout on your screen. Now we will check one by one. First of all, if you have to zoom into a particular portion of the layout, first you do a left mouse click and then you do a right mouse click. So to form the box where you want to zoom to. and then you press Z on your keyboard. So see, we are zooming in. So first things first. So if you remember, we had set the input output pin mode as something as 1, and I had mentioned that 1 is setting the input output pins equidistant. So this is what, if you see, the input output pins are present equidistant. There is, we'll zoom little more by pressing Z. Now let's see which layer our input output pin is. So this is a, so to select a particular object, what you do, you move your mouse over that object. Don't click anything, just move it over there. You can see my crosshair is on the input pin, and then you press S on your keyboard. So you will see that object getting highlighted. And apart from the layout window which you are seeing right now, there is one more window, tick icon window, which you see up here. So in that tick icon window, when you do a what, that will actually show which layer is this pin in. So this is in metal layer 3. This is what we had set in the horizontal metal, IO horizontal metal. Similarly, when you go down, there is vertical pins. You move your cursor over the pin and do an S, and you take the tick icon window and do a what. Should be metal 4. So yes, it is in metal 4. So metal 3 and metal 4. So this was what we had set. And apart from that, if you see, there are these decap cells which have been arranged along the side rows and the border of the side row. These are the boundary. We also call it up as end cap cells. So, and then there is these cells. If you zoom in a little more, you can see what they are. These are the tap cells which we had set. So tap cells are basically meant to avoid the latch-up conditions which occur in the CMOS devices. So they connect the N-bill to the VDD and the substrate to the ground. So that prevents the latch-up in CMOS devices. And these tap cells, you can see there is this, they are not, you can see they are diagonally equidistant. This tap cell and this tap cell is diagonally equidistant. So this value has also been set. If you refer to the README, you can see which switch is used for the tap cell distance. And to bring to your consideration, this is floor plan. And as I had mentioned before, floor plan does not take into consideration the placement of standard cells. But standard cells are present here. The question is where? If you see this lower right, lower left, this dashed lines, you can see few boxes there. So I made a cursor, left click and right click, then zoom, use the arrow keys to traverse, zoom a little more. So there are a lot of this standard cells, that's why it's taking this long to. So we will do one more zoom. I think we can see, we can bifurcate. Okay, so let's see what these are. I will move over one of the boxes. I will do an S. So it's already displayed there. Sky 130 buffer. So this is a buffer. Similarly, this is a clock buffer. OR gate. So these are standard cells which have now been kept in the lower left corner. So this is all about floor plan. I would request you to do a little more, just play around with all these switches and see what effect do they make. Just change the input output pin from 1 to 0, but always ensure that it's always good to, if you're making any changes, you make the changes in the design related config file so that it's more flexible. So I will just center this design S and then a V. So this is our design, this is our floor plan. So next, I'll just close this quick, and yes.
Hello everyone. Let's look into the placement and routing stage of the physical design flow. So the first step and the very important step in this particular thing is to bind the netlist with the physical cells. Okay, so what does this exactly mean? So this means that let's say we have this particular netlist with all these gates, and the shape of these gates represent the functionality of these gates. Okay, so for example, if this is an OR gate, the shape of this OR gate determines that this functions as an OR gate. But in reality, we don't have shape something like this. But what we have shapes something like a box. So for example, you have this flip-flop, okay, which is a square shape over here. It's actually a box of square shape or rectangle shape. For example, you have this NOT gate, which is of some triangle and a circle over here, but in reality it's a box. It has got some physical dimension. It has got a width and height. It has got some width and height of this particular cell. Similarly, for this particular AND gate, if you see, this is the shape, but it has got a physical view of something like this. So in reality, it is not something like this, but it is a box in internal, where this particular box will function as an AND gate. Okay, and similarly for flip-flop 2, the flip-flop 2 is also a square box. Okay, so what we have done is we have taken the we have taken the views of this particular thing, of this particular gates, and given them a physical dimension, because that's what is actually present in the real world. In the real world, we don't have this kind of shapes, but we have square shapes and rectangle shapes. So we have taken these gates and given them a proper shape, a shape and size. So basically we have given them a width and a height. Okay, similarly what we'll do is we'll take each and every component of this particular netlist and give them particular shape. Okay, so this particular section of the netlist. This is the third section of the netlist, and this is the final fourth section of the netlist. So each and every component of the netlist has been now given a proper width and height, a proper shape, and these blocks are already have they do already have a proper shape. So let's not worry about that. And now what we'll do is we'll take these blocks and remove these wires. Let's talk a bit about this particular thing. So these things are present in a shelf, and let's call that shelf as a library. So a library is basically a place where you will find all kind of books. These are like books, and these are like different books that we have available in the library. Not only this, the library also has the timing information of this particular gate. For example, what is the delay of this particular gate, what is the delay of this particular gate. So all this information are present in a huge set, and it's called as a library. Though the library can be classified into two sub libraries. One library might consist of only of the shapes and size, and one library might consist only of the delay information, but let's call it as a library for now. Okay, so the library will have the following information. It will have the width, height of each and every cell. It will have the delay information of each and every cell, and plus it will have the required conditions of this particular cell. Okay, so for example, at what condition does the flip-flop emits the output, sends the input to the output, at what condition. So there is something called as when condition. So all this information are present in the library. Okay, so along with this information, it also has various shapes of this particular various shapes of this particular gates. So for example, in this particular scenario, if you see, this gate has got a fixed width and height. The library also provides you some options for this one. For example, there will be another option in the library of the same cell. This particular cell, let's say 2, functions as some give some functionality. Let's say it is an AND gate. This 2 will also function as an AND gate, but it will be slightly bigger in size. Okay, and the second difference between this particular AND gate and this AND gate and is that since it is bigger in size, it will have least resistance path, so it will be faster compared to this one. Similarly, you have other options as well. You have even bigger cells than this one. So this is even faster than this one. It is bigger in size and faster than this one. So basically, a library has got has got various flavors of each and every cell. So let's say for this particular cell, you have three different flavors of the same cell. You have two of a bigger size, lesser delay. You have two of a even bigger size and even lesser delay. So you have various flavors of cells in your library. We can pick up what we want to, based on the timing conditions and based on the available space on your floor plan. Okay, so this was about library, and we will be talking more about library, more about the size, shapes, and more about the timing information that the library consists in a separate section. Let's not get into those things over here. That's a separate video on timing. So we'll be talking about the library constructs and everything in a separate set of videos. But in general, in a broader sense, library consists of everything. It consists of cells, shapes and size of the cells, various flavors of the same cells, and the timing information, the delay information. Okay, so let's keep it to that level till now, and let's move ahead. So once we have done that, once we have given proper shapes and sizes to each and every gates, the next step is to take those particular shapes and sizes and place it onto the floor plan. So let's say what we have till now. So we have the floor plan. We have a well-defined floor plan with the input and output ports defined properly and placed properly. We have this particular net list. Okay, basically this is our design, this is our full design, and we have a shape and size given to each and every component of this particular netlist. So we have the physical view of the logic gates, and we have this particular floor plan. The next step is to place this netlist onto this particular floor plan. And how do we do it? Let's look into that. Okay, so now this netlist doesn't comes into picture, but this is what comes into picture. Though we have to follow the connectivity information from the netlist, but we have to take this one if in a case of physical design placement. Okay, so let's do that. So this is our floor plan, and this is the pre-placed cells that we already had from the previous slides. Okay, so let's keep it. So these steps are done in the floor plan stage. So the placement stage, the stage where we do the placement, that will make sure that this particular locations are not affected. They are not moved. They are kept as it is. And the second thing that it will take care of, that there will be no cells that will be placed in this area. Okay, so these two things we have to take care. Let's move on with the placement step. So you have this particular netlist, and we have to take the physical view of this particular netlist and place it over here. For example, we'll take this, let's say we'll take this first section. So if you see, this flip-flop 1 is close to input port D in 1, flip-flop 2 is close to D out 1. Okay, so let's place it in that fashion. So you have flip-flop 1 which is placed close to D in 1, you have flip-flop 2 which is placed close to D out 1. Okay, and you have this combinational cells which is placed close to flip-flop 1 and flip-flop 2. So let's do that. Okay, so you have this particular combinational cell which is placed close to flip-flop 1, you have this combinational cell which is placed close to flip-flop 2. So if you see, logical connectivity is being maintained, and since this particular section of the circuit interacts with D in 1 and D out 1, they are being placed close to wherever they are. Because if let's say D out 1 was over here, and if we had placed flip-flop 2 somewhere over here, then the time required for this flip-flop 2 to communicate with its own D out 1 would have been huge. So we have been taking care of that particular huge delay in the placement stage itself by placing the flip-flop 2 close to D out 1 as far as possible. Okay, similarly we'll be doing for the next stage also. So let's say we have this particular section, D out 1, D in 1, flip-flop 1, flip-flop 2, D out 2. So we have taken this particular section and placed it over here. We have put flip-flop 1 over here and placed it close to D into, not exactly close to, but there are some reasons why we placed it close to flip-flop 1. We'll come to that in some time from now. Okay, flip-flop 2 is being placed close to D out 2, and there is a peculiar case over here where we have abutted the cells, the combinational cells. So now if you see, the delay between flip-flop 1 and 1 will be very minimal. The delay between 1 and 2 will be minimal. Similarly, between 2 and FF2 it will be very minimal. Okay, so we have done this on due to some reasons, and we'll be coming to those reasons in some time from now. So what we'll do is, since we have already placed two sections of the logic and I'm already running out of time, we need some more amount of discussions for this section and this section and the other place where we are identifying the reasons why we have placed D into in such a huge distance, and how do we place the remaining ones. So let's try to cover all of them in the next video. Thank you. Hello everyone. Let's continue our discussion on the placement of the cells. So we have done with stage 1 and stage, basically this stage of the design and this stage of the design. Let's continue with the remaining set of the design. Okay, so we have this blue colored logic, which is flip-flop 1 to some gates and flip-flop 2, and flip-flop 1 is supposed to be close to D in 3. D in 3 is placed somewhere over here. Okay, and flip-flop 2 is placed close to D out 3, and D out 3 is placed over here. Okay, so let's do that. What we'll do is, since we know that there is a huge distance, or there's a huge gap between D in 3 and D out 3, unlike we had D in 1 and D out 1, which was placed on the same lines. In this case, it's like it's completely diagonally opposite to it. So let's see what we can do. Okay, so we have this flip-flop 1 which will be placing close to D in 3. We have the flip-flop 2 which we are placing close to D out 3, and the logic at some intermediate distances. Okay, so now what to do with this particular huge distance and all, we'll come to that point in some time from now. But let's now just place it something like this, so that the logic is placed diagonally. The output flop is close to the output port, the input flop is close to the input port. Let's do it in this way for now, and we'll see what can we do. Okay, and the next logic is the green color ones, which has got the flip-flop 1 which is close to D in 4, and the D in 4 is placed somewhere over here, and the flip-flop 2 is close to D out 4. The D out 4 is placed somewhere over here. So again, there is a diagonally opposite IO ports, and where in the center you have this big bunch of logic where you can't place any of these cells. So this is an even difficult situation than the previous one. Let's try to solve that as well. Okay, so we'll start with flip-flop 1, flip-flop 2, and the intermediate logics. So let's place the flip-flop 1 over here. Though it seems to be a bit at a far distance from D in 4, we'll see what can we do about this distance. Okay, flip-flop 1 to 1 is at this distance, 1 to 2 is still at a higher distance, 2 to flip-flop 2 is still okay, and flip-flop 2 to D out 4 is still okay. Okay, so the logic starts from here, it goes all the way around this thing and comes over here. So this is a bit bigger problem for us to solve. So now that we have done with the placement, now let's try to solve the problems that we just discussed, the problems of this particular distance. And that problem, the solution to that problem is referred to as optimized placement. Okay, so what does optimized placement does? So now what we'll do is we'll do some estimations. Okay, and the estimations is that we'll estimate what will be the, we'll take an example of from let's say flip-flop 1 to D in 2. Yeah, flip-flop 1 to D in 2. Let's take this example. We will estimate the wire. In reality, there will be some wires. There will be a wire which will be going from this way, something like this, and connecting to this flip-flop 1. Okay, so before even going into the wiring stage, before even routing the design, what we'll do is we'll try to estimate the capacitances. So if let's say if there was a wire from this point to this point, the capacitances, which is epsilon A by D, and the area is basically the completely overlap area. So in this case, the wire area will be the actual area. So if you look into the capacitances from this point to this point, that is very huge, because it's a huge length of wire. And in fact, even the resistance, which is R is equal to rho L by A, since because you have a huge length, there will be huge resistance from D into to flip-flop 1. Okay, and what does that will do? So in general, if you see, if there is a person who is standing over here and there's a person who is standing over here, and if this person sends a signal or this person shouts, it will be very difficult for this person to listen to D in 2 because of this huge distance. Okay, in other words, what we can do is in a very simple solution, what we can do is we can place some person over here, we can place somebody over here, this person shouts to this person again shouts to flip-flop 1, but again there is some amount of distance, there will be loss of data. So what we'll do is we'll place we'll place somebody over here as well. So this person now sends a signal to this person, this one sends to this one, and this one sends to flip-flop 1. So whatever has been told by D in 2 is now being successfully retained and sent to flip-flop 1. This is called signal integrity. Okay, to maintain the signal integrity, we need someone at the intermediate steps who will reproduce what this guy is trying to say. And that's what basically comes the concept of repeaters. So repeaters are basically buffers that will recondition your original signal, make a new signal, and which replicates the original signal and send it again. Okay, this repeater will again reproduce its original signal and create a new signal and send it to the following stage. In that way, the signal integrity is maintained. Okay, so we solve the problem of signal integrity by adding some extra repeaters or adding some extra buffers, but there is a loss of area. So more and more repeaters, there will be more area which will be occupied on this particular complete floor plan. So that we have to still live with if we want to retain the signal integrity. Okay, so let's move on. We'll see where we will be needing the buffers and repeaters. Okay, so we'll start with the first stage. The first stage is flip-flop 1. It's close to D in 1, flip-flop 2 close to D out 1. Okay, so assuming that there is a person who is sitting over here, and assuming the listener is sitting over here, this is the sender and this is the receiver. So this port sends some signal, and it has to cross a distance which is quite decent enough to cross. Okay, so whatever this sender sends, the flip-flop 1 is able to receive without any deterioration. So signal integrity is maintained between the input port and the flip-flop 1 input pin. Okay, next from flip-flop 1 to 1, this distance also seems to be very okay. And let's say if we do all these calculations, we estimate the wire length, whatever we just talked about signal integrity, that is based upon some wire length estimation and calculation. So based on the estimation of what will be the wire length, there is some capacitance calculation, and based on the capacitance calculation, there is a waveform that gets created, and that waveform the transition of that waveform should be in a permissible range. So that's how we calculate, that's how we decide whether the signal will reach from this point to this point. So this thing, whatever we talked, will be covered in a timing analysis section, which is coming just after this section. Okay, where we'll be talking about transition analysis, data slew analysis. Okay, we'll talk about that. So basically, the slew is basically dependent upon the value of the capacitor. The higher the value of the capacitor, the amount of charge required to charge the capacitor will be high, and the slew will be even bad. So based on that, we estimate whether the signal will be able to reproduce correctly in the receiver stage. So based on those analysis, which we'll be doing in the upcoming videos, we decide that the distance between flip-flop 1 and 1 is reasonable enough. Now we see the distance between 1 and 2, and we see that it's reasonable enough. So this becomes the sender, this becomes the receiver, and the signal integrity is being maintained. Okay, now let's say 2 is the sender, flip-flop 2 is the receiver, and again the signal integrity is maintained, and we don't need any repeaters in between these two logic gates. Similarly, we go from flip-flop 2 to D out 1, and we see that okay, there's a reasonable amount of distance maintained between flip-flop 2 and D out 1. The capacitance is sufficient enough for the signal to maintain its integrity, and hence there is no need of repeaters. Okay, let's look into a second stage. Let's look into the stage of flip-flop 1, the yellow colored flip-flop 1. In this case, what you see is the D in 2 is placed at a far distance from flip-flop 1. Okay, and based on the capacitances, based on the estimated wire length and capacitances, we come up with some value saying that the slew is basically transition. The signal transition goes beyond certain limit, and if it goes beyond certain limit, the signal which is present over here, it's very difficult to reach this signal over here in the same condition as that of the input slew. So what we'll do, as we discussed, we'll place some repeaters. So we estimate that this wire length is huge enough, we estimate the capacitance is huge, and therefore we need to break this particular huge length, and we break them using some repeaters. So we added the first repeater. Okay, so the signal which is present over here will be sent to this now this will be your sender, this will be your receiver. Initially this was the sender and this was the receiver. So now this is the sender, this is the receiver. You send the signal from D into it gets received by the buffer. The buffer again reproduces it and sends it to the next buffer. This next buffer again reproduces it and sends it to the flip-flop. So in this way, now the long distance has been cut down to shorter distances, and now whatever D into is sending, the flip-flop 1 will be receiving it in a proper integrated manner without any deterioration, with the help of this particular repeaters or buffers. Okay, so that's the job of the buffers. And if you go on to the further logic, it seems that there is absolutely zero delay between, or very negligible delay between flip-flop 1 to 1 and flip-flop 2 and D out 2. So we don't need any buffers or any repeaters in this stage. Okay, so in this way what we'll do, we try to maintain the signal integrity, and we have still two stages to go. So what we'll do is, since I'm already running out of time, we'll try to optimize the placement for the remaining flops, and try to come up with some ways of how to optimize it with the help of some minimum amount of repeaters. So let's try to do all this in the next video. Thank you. Hello everyone, let's continue our discussion on optimizing the placement condition. And once we are done with the placement optimization step, the next step is to do a quick timing analysis with ideal clocks. Basically we need to do a timing analysis with the existing placement op condition. Okay, so let's begin. We already finished, we already discussed a bit about the placement optimization for this set of logic. Let's try to cover it even more in more detail over here. So you have this particular buffer which was placed, and the reason this buffer was placed was D in 2 was at a significantly large distance from flip-flop 1. Okay, so whatever D in 2 speaks, FF1 is supposed to hear it in the same condition. So in order to reproduce what D in 2 has sent, or in order to reproduce the signal that D in 2 has sent, we have placed this particular repeaters in the center. Okay, so these repeaters will take the signal from D in 2, repeat it or recondition it, or basically reproduce the same signal and send it again. This buffer will again reproduce the same signal and then send it again. So in this case, whatever signal conditions was there at D in 2, that will be getting faithfully reproduced at flip-flop 1, at the input of flip-flop 1. Okay, so that was the purpose of adding these two buffers. Next, when we move on from flip-flop 1 to the next logic, or which is this particular gate, since these two are sits very close to each other, there might not be any problems for reproducing the signal that is being generated by flip-flop 1 and send it to the logic 1. And the same condition exists for the connection between 1 and 2. So basically this is called as abutment. We have abutted certain logic so that there is actually no time delay between the signals which is getting passed from this point to this point. Okay, and there are multiple reasons to do this abutment. The one of the reasons is, let's say this particular section of your circuit works at very high speed. So in that case, what we do, we bring those set of logics very close to each other and make sure that there is absolutely zero delay when sending the signal from flip-flop 1 to flip-flop 2. Okay, so let's say this works at 2 gigahertz or something. So in that case, we don't want to waste delays on the wires, and as a result of that, we have abutted this particular cells. So this is a very classic example of high frequency circuit. Next, the flip-flop 2 has got some signal which is sent out to Dout 2 with a minimal delay, with a minimum delay. So the wire delay from flip-flop 2 to Dout 2 will be wire length will be very less, and as a result of that, the delay will be very less. So this piece of logic looks to be taken out of a circuit that is working on a very high frequency. Okay, next, moving on to the next set of circuit. So let's say we have this blue colored circuit. So blue colored circuit, we have the D in 3, we have D in 3 over here, and we have Dout 3 somewhere over here. Okay, so let's look into the conditions. So D in 3 is placed at a sufficient distance from flip-flop 1. We might not need the flip-flop. We might not need a repeater somewhere over here, because it's a reasonable distance to reproduce the signal. And these conditions are being calculated based on the transition value, or based on the slew value, which we'll be talking about once we finish the optimized placement. Basically, once we move into timing analysis for ideal clocks, we'll talk about what is the acceptable marginal condition for the signal to be considered as a real signal, or as a sufficient signal to trigger the flip-flop 1. Okay, we'll talk about that. So D in 3 to flip-flop 1, we might not need any buffers. Flip-flop 1 to 1 also, we might not need any buffers, because this looks sufficiently less distance, or reasonable distance. From 1 to 2, we also might not need any buffers, because looks like it will be able to send the signal faithfully to the logic 2. Okay, from 2 to flip-flop 2, it looks a bit high. The distance looks a bit high based on the analysis that we will be doing sometime from now. Based on the slew analysis or the data transition analysis, looks like the distance between 2 and flip-flop 2 is a bit high. So we'll place a buffer over here, and now the distance between 2 and buff is one of the distance, and from buff to flip-flop 2 is another distance. Okay, and finally we have the flip-flop 2 that moves to Dout 3. So you have flip-flop 2 to Dout 3, which also is placed sufficiently close to Dout 3, and hence we don't need any buffers in this area. Okay, next, the final logic we have. So we have d in 4. This is a bit tricky. Let's see how do we solve it. So d in 4 is placed somewhere over here, okay, and d out 4 is placed somewhere over here, and you have and then the signal has to traverse right from this point till this point. Let's do that. So from d in 4 to flip-flop 1, the distance looks a bit high. It looks a bit on a higher side. Okay, so you need to place some buffers, and you can't place buffers in this area because this part of the floor plan is already occupied by decoupling capacitors and blocks and so on. So you can't place a buffer in this area. Let's try to route it, or let's try to place the buffers from this path. So we'll add one buffer over here, and then now the distance from d in 4 to buffer looks significantly less, and looks like the d in 4 signal will transfer to buffer input with the same slew conditions. Okay, and moving on from buffer to flip-flop 1, it still looks okay. We don't need any extra optimization to be done in this area. From flip-flop 1 to 1, this distance also looks okay. The only problem that we see over here is there is a kind of crisscross. Okay, so you have buffer to flip-flop 2 over here, you have flip-flop 1 to 1 over here, and these are very normal conditions in a placement and routing tool. We will be taking we'll be connecting this flip-flop 1 to 1 in a separate layer. We'll be trying to connect this buffer to flip-flop 2 in a separate layer. So we'll talk about a bit of placement and route algorithms, not in this section but in a separate section. We'll talk about that in some time, in a few slides from now. So we will so there are crisscross, but we will find out a way to fix this in a routing stage, where we take this connection from this point to this point in a separate layer, let's say metal 3, and we take this connection from this point to this point in a metal 4. You can think currently you can think of it in that it will be a different layers. Okay, next you have this connection from this point to this point. Again, if you see, the distance is a bit high, and also there is a logic which is sitting over here, and this again a normal condition. And the way the routing might happen is the flip-flop 2 is in the internal routes of the flip-flop 2 might be in some layer, let's say metal 1, metal 2, and the connection from the signal connection from 1 to 2 will be on a separate layer that will be like metal 3 or something of that sort. Okay, so this distance still looks a bit high, so let's place a buffer over here. Okay, and then now let's route from 1 to buffer and buffer to 2, and finally from 2 to you have this flip-flop 2, and then flip-flop to d out 4. So we have done a significant amount of buffering in this area, and all basically complete logic is being now optimized based on the placement condition. Okay, so next what we have to do is we have to check what we have done is correct or not. So for that, now since the clocks are not built, what we have to do is we have to just check the data path over here. So considering there are no clocks, or considering the clocks are ideal, by ideal clocks we mean that the time required for the clock 1 to reach flip-flop 1, flip-flop 2, any of the flip-flops is 0. So based on the ideal conditions of the clock, let's try to quickly do a timing analysis. Okay, a setup timing analysis, a hold timing analysis, and not hold, basically. So hold will not make any sense once we don't have the clock. So let's try to do a quick setup timing analysis with ideal clocks. Okay, and based on the setup timing analysis, or based on the numbers that we get out of the setup timing analysis, we will come to know whether the placement that we have done or not is reasonable. Okay, so based on the numbers, based on the frequency, or based on the specifications that has been given to us, and we'll also note down some specifications. So based on the specifications, we have to check whether this placement condition is meeting those specifications. If not, then we have to see what we can do, because if it doesn't meets at this stage, it's bound to get bad when we go to further stages of placement and route, or basically route stage. Okay, so let's try to do the setup timing analysis for ideal clocks in the next video. Thank you. Hello everyone, let's continue with the need for characterization topic. So let me take you through a typical IC design flow that every design needs to go through if it wants to be implemented onto a chip. So the first step to do that is logic synthesis. So for example, if you have a functionality which is coded in the form of an RTL, the first step to convert the functionality into a legal hardware is referred to as logic synthesis. So the output of logic synthesis is nothing but an arrangement of gates that will represent your original functionality that that you have described using an RTL. Okay, that's the first step of an IC design flow. And why are we talking about logic synthesis in the library characterization course? So I'll get back to that in a minute from now. But the output of the logic synthesis are nothing but gates, the flip-flops and the gates, and the proper connections of the gates to represent the original functionality. So that's what logic synthesis is all about. The next step of the logic synthesis is nothing but floor planning. In this particular step, we import the output of logic synthesis, or we import the netlist that we get out of the logic synthesis, and decide the core and decide the size of the core and the die. Okay, so the sizes or the width and height of the core and the die is completely dependent on the amount of gates and the shapes and sizes of the gates present in the output of the logic synthesis step. So that's when the floor planning stage comes into picture. And why are we again talking about floor planning step in the library characterization course? So I'll again get back to that in a minute from now. The next step after floor planning is placement. So in the placement stage, we take this particular logic cells present over here and place it on the chip in such a fashion that the initial timing is met. For example, the flip-flop 2 is close to diode 4, so we prefer the flip-flop, in this case the connection shows that your flip-flop 1 or the flip-flop 2 which was present over here was close to diode 4, so we prefer to keep or place the flip-flop 2 cell close to diode 4. Similarly, we prefer to keep the flip-flop 1 over here close to DIN1 because logically it is being connected to DIN1. So as a result of that, you will be able to meet the timing between DIN1 and flip-flop 1. We also prefer to keep the logic cell 1 close to flip-flop 1 because in your logic synthesis netlist, it is basically connected to the flip-flop 1. So it makes sense to keep it close to keep it as close to as possible. For example, if it is not possible to keep it close to cell, we place it apart. For example, in this case, flip-flop 2 is present over here, flip-flop 1 is present over here, your DIN2 is present over, your DIN3 is present over here, your DO3 is present over here. So for some reasons, it's not possible to keep them close by, but we spread them apart based on the functionality or based on the logical connection that we get out of the logic synthesis step. We will take care of these things by adding buffers and so on, but the typical step after the floor planning step is the placement stage. Now, why are we talking about placement stage in the library characterization course? Again, I'll get back to that in a minute from now. There will be one common thing across all these steps that we do over here, and I'll get back to that in a minute. So the next step is the clock tree synthesis. So for example, if you want to have a zero skew, if you want to have the clock being spread across the logic cells at an equal time, so for example, the flip-flop which is sitting over here and the flip-flop which is sitting over here should receive the clock at exactly the same time. That's basically called as clock tree synthesis. So clock tree synthesis stage, we basically an H tree that will take care of the clock signal reaching at each and every clock endpoints. And also the buffer cells, all the clock buffers that you see over here, they will take care that the clock signal has got equal rise and fall time. So that step is referred to as clock tree synthesis stage. And this is again a stage which is very, very important and very much related to the library characterization step. So I'll get back to that. Finally, if you do a routing stage, so for example, if you want to route two cells, let's say if you want to route this cell with this cell, there is certain flow that the routing has to go through, and it's typically dependent on the characteristics of this flip-flop and the one. So for example, if you want to route from this point to this point, this is an example of the maze routing that we have explained in one of my courses called as physical design flow. So this is the one of the examples of maze routing. If you want to route from this point to this point, there are certain properties of the cells that has to be taken care while routing from this point to this point. And I'll very much be able to show you how this routing step is also related to your library characterization step. And finally, if you want to do a static timing analysis is a step where you try to see what is the setup time, what is the hold time, what is the maximum achievable frequency of a circuit. So for example, if you have a launch flop, capture flop, and if you see this particular equation that represents what is the data arrival time and what is the data required time, and this is an example of an hold violation. So you might want to go through one of my STA course to understand the static timing analysis part over here. So in all these steps, the STA step is basically the last stage in an IC design flow. Basically, this is called as a sign of STA stage or the sign of timing analysis. So in all these steps, and one thing is common across all these stages, and that thing is nothing but your gates or cells. So if you see, if you have an AND gate, you have an OR gate, buffer, inverter, D flip-flop, latch, ICG, all these are common across all these steps. and that's where your library characterization step is really very important. And why is it so important? This collection of gates is referred to is this collection of gates, if you place in some area, that area is referred to you as your library. So the question is, how does this particular stages uses this particular gate? So this gates has to be represented in such a fashion to the tools that the tools understand what these gates are. Okay, I mean, when we draw on the paper, it's just a two input AND gate, it's just a two input OR gate, and so on. But if you want the tool, the EDA tool, to understand what this gate is and what are the timing characteristics of this gate is, we need to model these gates in such a fashion that it is understood by the EDA tool. So how the question is, how do we design, characterize, and model these cells? And the answer to that is, welcome to my new course on library characterization. So what we'll do is, we'll stop at this point, and from the next video we'll look into a typical cell design flow. So let's stop at this point, and let's start from the cell design flow from the next video. Thank you.
Next stage post floor plan is the placement stage. So if you remember, I had told you that placement, we are doing a congestion related placement. So we are not right now considering the timing. So we are just ensuring that the congestion is less. So, and there were three settings, if you remember, for placement. We will do run. So placement in OpenLane occurs in two stages. One is a global placement and the second is a detailed placement. So there are different tools to do both of these functionalities. So global placement is basically a course placement, more of a course placement, and there is no legalizations happening. So legalization happens in detailed placement. So what is legalization? So the standard cells are placed in standard cell rows. So they have to be exactly inside the rows, and they should be abutted with each other. So, and there should be no overlaps. So this is what a legalization is. So a legalization is more required from the timing point of view. So these are some concepts which you would want to explore. Now when I do a run placement, so I told you in a run placement, the first this global placement happens. So global placement, the main objective is reducing the wire length, and in OpenLane we use a concept of HPWL, that is half parameter wire length. So the reduction of half parameter wire length is the main focus. So this should take some time. So if you see these iterations happening, and if you see this half parameter wire length, and below that something called an overflow. So our objective is to converge this overflow. If the overflow value decreases, that means your design will converge. That means the placement is going right. So our design did converge. This is what I told about the legalization. So everything was okay, there was no overlap. So the placement is done. So we would want to see how our design is post placement. So if you remember, I had told you placement is where the standard cell positions get fixed. So we will move one level up and go to placement. Just there is this def file created. We will just see how our design looks right now. So just as before, we will do magic -t. We will use the same text file, left file, def read, everything. Commands will be same. For def read, we will use this, and then ampersand. Now this is something interesting. All those do S centralize, all those standard cells. So these many standard cells were actually at the lower left corner in the initial layout of the floor plan. If you zoom in, you can see the placement of the standard cells in the standard cell rows. So this is what placement stage is all about. There are no DRCs. all the standard cells are now placed in the standard cell rows. Floor plan ensured that there is decap at the boundaries of the standard cell. The tap cells are properly placed, the IO pads are correctly placed, and placement ensured that the standard cells are correctly placed in the standard cell rows. So we'll do an S, we'll do V. So the next exploration task is up to you. Just play around with the floor plan and the placement switches, and the MCQs that will follow will relate to this. So yes, before moving to CTS, we need to do with this floor plan and placement. And before we conclude this lab session, I would like to point out that this power distribution network, that is the power ground network, gets created during floor plan. That should be created during floor plan, but in OpenInflow right now the order is little different. So the floor plan does not create the power distribution network. A post floor plan and post placement in CTS, post that we do PDN, power generation, power ground generation, that is a PDN network generation. This before the routing. So we have not done power ground as of now. We will keep that post CTS. So this is all this lab session was about. Yeah, happy learning. All the best.
Hello everyone, let's go through the cell design flow. So let me recap a bit over here. So for example, if you have this placed and routed chip over here, so the design, the logic synthesis step that we have presented in the last video, for example, this particular thing is a placement and routed version of the logic synthesis step. So you have this flip-flop 1, 2, 3, 4 and all of them connected. So you have the D in 1 to flip-flop 1 when properly routed, you have the flip-flop 2 to D out 4 being properly routed, and so on. So you have these steps already done over here. So out of this particular typical placement and routed design, let me show you something. So if you pick up any of these cells over here, let's say you pick up the flip-flop 2, if you pick up the buffer, if you pick up this particular gate which is named as 1, they are referred to as standard cells. Okay, now this key or this term is really very important for us, is the word which is called as standard cells. Standard cells are nothing but in a typical IC design flow, we call these buffers, this inverters, this AND gate, OR gate, all of them as standard cells. Okay, now a standard cell is being placed in a section called as library. So for example, the library is a place where we keep books, where we keep lot of books, where we keep variety of books. Similarly, in an IC design flow, a library is a place where you keep all your standard cells. It can be even extended to more things, like a library is also a place where you keep all your decap cells, you keep all your macros, IPs and so on. So library, one of the sections of the library is to keep the standard cells or to place the standard cells over there. Okay, so this is a typical area in an IC design flow where you keep all your gates and so on. Okay, so if you look into the library, it has got an AND gate, OR gate, buffer, inverter, D flip-flop and latch and ICG and so on. But this is not all. If you see this particular library has got something more to it. If you open up the library and see, the library definitely has got different gates with different functionality. For example, AND gate has got a different functionality than the buffer and so on. So it definitely has got cells with different functionality, but it also has got the cells with different sizes also. So in this case, this OR gate is of a different size than this one. This OR gate is of a different size of this one. Okay, so the library has even that information as well, and those are the physical characteristics of the library. So if you, let's say if you take a buffer, for example, buffer is of a different size of this over here. It has got of a different size over here, and it is of a different size over here, and these sizes are referred to as drive strengths. So for example, this is a bigger buffer, this must be strong enough to drive a wire compared to this buffer or compared to this buffer. This is the smallest buffer, this is the least drive strength buffer. So that is what the functionality, or that is what the characteristics of a library is. A library has got cells with a different functionality and different sizes, and that's not all. It has got cells with different threshold voltage also. So for example, this inverter will have a different threshold voltage than this inverter. So for example, this inverter might operate at, let's say, 0.3 volts of threshold voltage. This inverter might operate at 0.4 volts of threshold volt. So the variation in threshold voltage decides the speed of your cell. So for example, 0.4 threshold voltage inverter will take more time to switch compared to a 0.3 voltage threshold voltage inverter. Okay, so that's the difference between the having a different threshold voltage, having a different variety of threshold voltages in your library. And the more advantage if you see of this particular threshold of this particular varied VT cell is whenever you do a leakage power recovery. I'll get back to those steps in a moment from now. For example, for now, let us try to understand what does this library consist of. So the library consists of cells of different functionality, not only of different functionality but of different sizes and of different VT. So for example, so this inverter is of different VT than this inverter. So let's say, for example, that's why the colors are different. This inverter may be of a different VT than this inverter because of the difference in color. And also it's possible they are of the same size. For example, this inverter is of the same size of this inverter, but they are of different VTs. So this is the basically a function or a place, or this is called as a library, and the library has got all these things. So the next step is to look into, let's say, if you take into one of the inverters, if you take this particular inverter, you will be amazed to see the cell design flow. You will be amazed to see how does this inverter is coming into picture, so that it is basically understandable by a typical EDA tool. So for us, this inverter is nothing but a single input cell, but for an IC design flow, this inverter has got something else to do with it. The inverter has to be represented in form of its shape, in form of its timing behavior, in form of its drive strength, in form of its power characteristics, and so on. So this small inverter has to go through a typical cell design flow, and I'll very soon fill up this particular table over here. But the point over here that we are trying to show that the inverter, a cell as small as an inverter, has to go at typical steps of a cell design flow, and that's huge. And you will be amazed to see what are these particular steps. So let's look into those steps. So the steps, the cell design flow is being divided into three parts. One is the inputs. So basically these are the inputs that you need to design your inverter, and then you finally design your inverter, and the outputs of the inverter are the ones that you actually use by your EDA tools, that is actually used by your EDA tools. So let's look into all of them one by one. So we'll start with the inputs. So for example, let's take an inverter only for an example, and the inputs to design the inverter are basically, to start with, those are called as process design kits. So these are something which comes from your foundries, and the foundry provides the process design kits. In the kits consist of the DRC, LVS rules, SPICE models, and library and user defined specs. So I'll show you each one of them one by one. Okay, so there is nothing called as inverter over here, but we have to design the inverter based on the process design kits that is being given by the foundry. So let's look into each one of them one by one. For example, if you look into the DRC and the LVS rules, if you go through one of my courses, it's called a custom layout course. You might want to go through it. You will be able to see a lot of DRC and the LVS rules over here. But let me give you a brief idea over here. So for example, if you look into the tech file, that it basically provides you a tech file with some rules. So for example, over here the rules are, if let's say this was a polysilicon, this was your contacts, this was your n-type substrate, this was your n-type substrate. So the typical rules basically say that the design width or the poly width, this particular width, has to be 2 lambda. The extension over active, for example, the extension over active area. So in a layout, basically you call this as an active area. And why it is called as an active area? Because this is the place where you place your transistors. So these are all the snippets from one of my previous courses, custom layout. So you might want to have a look into that course. That course explains in details what each and every layer is. So if this is the active area, your poly extension over the active is the design rule specifies it's to be 3 lambda. So these are the typical feedback, or these are the typical inputs that we get from the process design, that we get from the foundries. So foundries have already done all these experiments, and with those experiments they have come up with a rule that your extension over active has to be 3 lambda. If it goes below 3 lambda, the foundry will not be able to fabricate that particular poly. Okay, that's where these rules come into picture. So there is one more rules. For example, the poly to active spacing. So if you see the poly to active spacing, that is it is expected to be 1 lambda. So what the value that you put as an actual value is basically the drawn value, but in this case the value that the foundry specifies is basically mentioned over here. It's called as a design rule. So these are some of the rules I have just shown over here. The 3 rules. There could be thousands of rules. For example, the rules could be coded in something in this fashion. Okay, so there could be more than thousands of rules present over here that has been given by your foundry, and that has to be followed in a typical IC design flow. Okay, so these are the part, this is one of the inputs that you get from your foundry. The next input that you get from your foundry is spice models. So for example, if you look into the drain current equations, if you look into your threshold voltage equations for your inverter, you will see something like this. So if you look into a threshold voltage equations, it basically is called as the initial threshold, the threshold voltage without the substrate, and plus gamma 1 minus 2 phi plus VSB. These are all basically equations taken from one of my courses called as circuit design and spice simulations. You might want to have a look into in that course to understand where are these formulas coming from. So if you look into the threshold voltage equation, it has got a parameter which is called as the foundry parameter. If you look into this parameter, this is again a foundry parameter, because the 2q Na epsilon Si, these are all standard values that you get from the foundry. Okay, similarly over here, so these are small, the parameters that you see, the one which are encircled over here, these values are the ones that you get from the foundry, and these are referred to as spice model parameters. Okay, so based on the spice model parameters, these are again one of the inputs that you get from your foundry, and based on the spice model parameters, I've just shown a handful of parameters over here. These parameters are spread across the table, so there could be thousands of parameters present over here. I've shown some example over here. So for example, these are all the parameters for your NMOS, these are all the parameters for your PMOS. If I want to show you one of the parameters, for example, COX, your oxide capacitance is epsilon ox by TOX. Your TOX will be given over here. So your TOX is 5.8 nanometers. Your TOX is 5.8 nanometers. For example, VTO is the threshold voltage in the absence of bias. So VTO will be given over here. If you see over here, VTHO is 0.5 volts, is negative 0.5 volts for PMOS. It's over here. It's negative. It's positive 0.39 volts for your NMOS. Okay, so these are the typical spice model file. We call it as a spice model file, and also it has got all the capacitances value over here. So if you see, it has got CDS, all the ones which are starting from C, those are all capacitances. Similarly over here, so these are called as spice model file, and those are again being given by your foundry. You have to use these spice model files, this DRC and the LVS file in as an input from the foundry, and design your system or design your inverter in such a fashion that that the inverter that you have designed, those follows this particular rules given from the foundry. Okay, and finally you have the library and the user defined specs. So what we'll do is, since I'm running a bit late out of time, let's stop at this point and let's start from the library and the user defined specs from the next video. Thank you. Hello everyone, let's continue with the library and the user defined specs. So let me give an example of an user defined specifications. In this case, the cell height is been defined by the separation of the power and the ground rail. So in this case, if you see this laid out design, this is the power rail, this is the ground rail, this is the power, this is the ground, and so on. So this is how a typical chip design flow works. So the separation between the power rail and the ground rail decides the cell height, and it is the responsibility of the library developer that the cell height is maintained. It goes neither below this or above this. Okay, the cell width is dependent on the timing information. For example, this is an information given to the library developer that we need cells from drive strength 1 to X. So it's a responsibility of the library developer to decide or to design cells which has got a drive strength from 1 to X. So lower the value of the drive strength. Lower the value of the drive strength. For example, if the drive strength is 1, it will be very difficult for that particular cell to drive huge wires in comparison with the higher the value of the drive strength. For example, if a cell has got a drive strength of 10, it will be able to drive even more longer wires. That's called higher drive strength cells. So this drive strength decides the cell width, but the cell height is decided by the separation between the power and the ground rails. Okay, let's take another example of the user defined specifications. For example, supply voltage. So a typical inverter has to operate at a certain supply voltage which is being provided by the top level. Okay, so the top level designer decides on what is the supply voltage will this chip operate on, and accordingly the library developer has to take that supply voltage and design the library cell in such a fashion that it operates at this particular supply voltage. He has to take care of the noise margin levels with respect to this supply voltage. So that's basically another user defined specifications. Next, let's say metal layer. So for example, if there is a specification that certain libraries has to be built on under certain metal layers itself. For example, in this case, we have a poly layer, we have an active layer, and this is the metal one layer used for power ground rails. In some cases, there might be a requirement that the metal layers or the power layers or the contacts should be built on metal 3, 4, and 5 layers. So that's the metal layers requirement, and that is again one of the user defined specifications for your library cells. Finally, you have something called as pin location. So the library developer needs to decide on the pin location. So this, I've located the pins over here and here. There might be a requirement that the pin should be near the power and the ground rail. So for example, there could be a pin location which is present over here. There could be a pin location that has to be present over here, and accordingly the library developer has to adhere to those rules, and those are some more user defined locations, or those are some more user defined specifications. And some more if you have the drawn gate length. So for example, for a typical gate length of 130 nanometers, let's say the drawn gate length could be 125 or 135 based on the library and the user defined specifications that has been given to us. Okay, so these are the typical examples, or these are the classic examples of user defined specifications. Let's move on with the design steps. So now, since we have all the inputs with us, it's now available with the library developer. It's now the responsibility of the developer to take these inputs, and based on these inputs come up with a library cell that adheres to these inputs. Okay, so that when this particular library cell is getting plugged into the top level designs, like into the CTS stage or into the placement stage, into the routing stage and so on, it should not be a problem for the physical design steps. So that's how important a library developer is. So next step is to design using this particular spec. So design again involves three different steps. The three different steps are circuit design, layout design, and characterization. Let me try to explain each and every step one by one. So for example, if you take the step called as circuit design typically involves some few steps, some 2 steps. So if you take the circuit design into example, the first step is to implement the function itself. That is the first step. And the second step is to model this PMOS and NMOS transistor in such a fashion in order to meet the library requirements. For example, the W/L P ratio and the W/L N ratio is expected to be certain, let's say 2.5. W/L of the P is equal to, let's say, 2.5 times of W/L. So in that case, you need to design the PMOS and the NMOS transistors in such a fashion that these values are being maintained. Okay, another example could be the W/L of the let's say the drain current, or the drain current equations I have not shown over here. So let's say the drain current has to some X microamps. So in order to get that X microamps, it has to be designed. The PMOS transistors and the NMOS transistors needs to be designed in such a fashion that you get that much amount of required current. So those are basically called as circuit design steps, and these are mostly based on SPICE simulation. So this is one of the examples from one of my courses on circuit design and SPICE simulation. So in this case, the requirement, the typical requirement is the drain current of the PMOS and the drain current of the NMOS. If you add them, it is equal to 0. So that's the standard case. When you try to make them to 0, you attain this in this particular equation, and with that particular equation, based on what value is needed. For example, if you need a certain value of the switching threshold, you keep that as constant, and you can design all of them based on keeping that switching threshold value as what you need. For example, in this case, if you need a switching threshold value of 1.2 volts, 1.2 volts is plugged over here, the VDD value is plugged over here, the threshold voltages are again plugged over here, and based on the equation, you come up with a value of W/L of the PMOS transistors as a multiple of W/L of the NMOS transistors. Okay, so this is basically a step which is called a circuit design. Next is the layout design. Once you come up with the steps of circuit design, for example, once you know the value of the W/L of the PMOS, W/L of the NMOS, next step is to implement that values into a layout, and that's basically called as the layout design. So before moving into the layout design, the typical output that we get out of circuit design is a circuit description language. It's called as a CDL file. So next step is the layout design. In the layout design has got certain steps. So the steps are pretty much elaborated. So what we'll do is we'll look into one step. The first step is to get the function implemented through a MOS transistor, through a set of PMOS and NMOS transistors. The second step is to get a PMOS network graph and the NMOS network graph out of this design that you've implemented over here. Okay, so the further steps to get the layout are a bit elaborated. So what we'll do is we'll stop at this point and we'll look into the more elaborated steps from the next video. Thank you. Hello everyone, let's continue with the more elaborated stages of layout design. So the first step is to implement the function itself using, for example, if you have been given this particular function, you need to implement this function based on the set of PMOS and NMOS transistor connections. So this particular set of transistors will represent this function. The next step is to derive the PMOS network graph and the NMOS network graph out of this. So if you look into a typical art of layout, it's an Euler's path plus stick diagram. So if you follow these steps, the layout that you want to derive out of this particular function will be giving you the best performance and the best area. So the next step is to, after you get your PMOS network graph and the NMOS network graph, the next step is to obtain the Euler's path. So in order to obtain the Euler's path, you might want to look into one of my courses on custom layout that will help you to get the Euler's path. Euler's path is basically a path which is being traced only once. So that's basically called as an Euler's path. For details, you might want to go into my custom layout course and have a look into that. So once you get the Euler's path for the PMOS and the NMOS network graph, so in this case the Euler's path is A, C, E, F and D and B. So based on this Euler's path, the next step is to draw a stick diagram out of it. So if you look into the right hand side, this is a stick diagram. A, C, E, F, D and B are nothing but the inputs, and these are nothing but the gate input. So you place the polysilicon A, C, E, F, D, B in that particular order, and you also make the connections which is being mentioned by your circuit. So this circuit which was present over here, based on the circuit connections or the circuit topography, you make the connections over here. In this case, for example, if you look into this one, if you look into the E input of your transistor, of your this transistor, this represents your NMOS, this represents your PMOS, and it says this is source, this is drain. It says your E input source and C input drain are all connected, or basically E transistor and the C transistor are all, the source and drain are connected, and your F transistor source and your D transistor drain are connected. Basically the PMOS transistors source and drain are connected, and this particular block means your A transistor source and your C transistor source are connected. That's why you see your contact over here, and this in turn is connected to your D input or the D transistor, D NMOS transistor drain and the B NMOS transistor drain. Okay, so this is how you interpret the stick diagram, or basically this stick diagram is being derived out of the circuit diagram or the circuit design that you did just in the previous stage. Okay, so the next step is to convert this stick diagram into a typical layout, into a proper layout, adhering to the rules that we have got from the input. So remember, sometime back we were looking into the layout rules in the PDKs. When we received this PDKs, we also got a DRC rules. So the next step is to convert the stick diagram into a layout while we adhere to the DRC rules which is being given by the foundry. So let's and also adhering to the rules and the user defined specifications which is being given by the top level user. For example, the drawn gate length is over here, the contacts is over here. For it might be possible that the contact placements or the pin locations has been given over here and over here, and that's the reason we have placed the pins somewhere over here. So that those are some of the rules or some of the user defined specifications, or those are the inputs that we got from our previous stages. And again, the metal layers. So for example, it has got metal 1, it has got polysilicon and so on. So this thing is being built on metal 1 layer, and it could be again taken up to the metal 2 or metal 3 layer depending upon the requirements that comes from the user or from the user defined specs. So that's a layout which is being drawn using the circuit that we have over here, and using the inputs or the DRC rule inputs that we got from the input stage or from the foundries. So that's the next stage. And finally, if you see, you take this particular hand drawn layout and put it into a tool. In this case, I have used a tool called as Magic, which is an open source tool. So I've drawn the layout using Magic, and this is the typical layout that you see out of this complete step. So this is the layout design part, and these are the different steps that you need to go while designing your layout. So these steps has been very much elaborated in my custom layout course. You might want to have a look into that course. So finally, once you have this particular layout, now you have the cell width, you have the cell height, you have the cell width over here, and in this particular layout will adhere to the drain current requirements and all the pin locations and all the user defined specifications that we were asked to do so. Okay, so this is your library cell. The next step and the final step that is remaining is, in this case, is to extract the parasitics out of this particular layout and characterize it in terms of timing. So before that, the output of the layout design will be GDS2. GDS2 is nothing but a typical layout file. Left basically defines the width and the height of the cell and the extracted spice netlist. So when we say about extracted spice netlist, it's nothing but the parasitics or the resistance and the capacitance of each and every element over here is been extracted out of this particular layout. Okay, so that's an extracted spice netlist, and which is again very useful information to do a characterization. So next step after this, after you get the extracted spice netlist and after you get the typical layout over here, the next step is to characterize this thing, and that's what this course is all about. So characterization is the step that will help you to get your timing, noise and power information, and the output of the characterization is nothing but timing, noise and power dot libs and the functionality of this particular circuit. So what we'll do is we'll stop at this point of time. From the next video we'll look into a characterization flow. So a typical flow, a typical cell design flow for an inverter has to go through all these complete steps. So inverter by definition it looks very simple, it's a single input gate, but the steps involved in designing this inverter is humongous. Okay, so the next step is to look into the characterization flow. So what we'll do is we'll stop at this point and we'll start looking into the characterization flow from the next video. Thank you. Hello everyone, let's continue with the characterization flow. So first of all, let me figure out what all things we have as of now based on the 3 different steps that we saw in the past video. So in the past video we saw 3 steps, like the input stage. For a cell design flow there was an input stage, there was a design steps, and there was output. So from the inputs and the design steps, let us figure out what all things we have. So let's say we have done the circuit design and we have done the layout design. So out of that, the inputs that is available with us are this one. You have the layout with you. Okay, so this is a layout of, let's say, a buffer. This is an inverter, and I have used open source Magic Layout tool to draw this particular buffer. So you have a buffer over here, or the layout of a buffer. You have the description of the buffer. So for example, 2 inverters connected back to back, you have the description of the entire buffer along with the power sources and everything that is getting connected. Okay, so you have this description as well. You have the spice extracted netlist. So whatever you see in this particular layout, you have this metal layers, you have this contacts and everything. So each and every element will have a associated resistance and capacitances with them. So we have extracted all of them in terms of a spice netlist. So in the spice netlist, you will see a lot of like capacitances and resistances over here. Okay, it's not been evident over here, but in a real spice netlist which has been extracted, or in an extracted spice netlist out of the layout, you will see a lot of resistances and capacitances statements over here. So that's called an extracted spice netlist. Finally, you have the inverter subcircuit. So if you see the lines over here, this is called X1 IN1 net, and there is one net and there is another net, and the subcircuit name is my INV. Again there is something called as X2, and the subcircuit name is my INV. So this subcircuit has to be loaded from somewhere. So I have included the subcircuit file over here, and this is how the subcircuit looks like. So the subcircuit actually contains the NMOS and the PMOS models. It has got the connectivity of an inverter. So this inverter being loaded twice. So what you see in this particular diagram on the right side, if you have this inverter is being called from this subcircuit, this inverter is being called from this subcircuit, and when you attach them both together in the form of a spice netlist, you get this description of a buffer. Along with the description of the buffer, you have this capacitances and resistances, which will give you a description of an extracted spice netlist of a buffer. So you have included you have the subcircuits as well. Now in the subcircuits you have the spice model. So you have the NMOS spice models, and as I mentioned in my past videos, the NMOS spice models or the spice models are nothing but the characteristics of the NMOS transistor. So you have the N channel behavior, or the N channel doping concentration over here. You have the VTHO. So this all things I have explained a lot in my circuit design and spice simulation course. So you might want to have a look into those courses. Most of them we have explained in that course. You have the level, the kind of simulation that you need to do, and you have a lot of things. If you go through the course, you will be able to figure out all of them, mostly all of them. Okay, so you have 2 different spice models. One is for the NMOS, one is for the PMOS. So these are the inputs that are available with us. So let us try to build the characterization flow based on the inputs that we have, and that's a standard characterization flow that is being followed in industries. So let's do that. So the first step is to read in the model. So we have to first of all read in the models, because this is the place where things start from. So you need to read in the models and also the tech file that is needed for the layout, but that comes at a very later stage. So the first step that comes out of the industries or out of the foundry is the model file. So the first step is to read the model files. The second step is to read the extracted spice netlist. The third step is to define or to recognize the behavior of the buffer. Okay, that's a really important step. The fourth step is to read the fourth step is to read the subcircuits of the inverter. So this is the subcircuit of the inverter that also you need to read in. and then you have the fifth step where you attach the necessary power sources. So for example, over here the VDD from this point and this point are being connected, and it has been connected to a VDD supply, and then this has been connected to the ground. So you have to read in the necessary power supplies. That is your fifth step. Your sixth step is to apply the stimulus. Now stimulus, we have varieties of stimulus, and I will be talking a lot about the inputs or the stimulus that is being given to the characterization setup. So this is called as a characterization setup. So that is a lot that we are going to talk about the stimulus, and that will follow this particular video. So this is the stimulus application which is being followed as a step 6. Next you have to provide the necessary output capacitances. So over here I have given an output load capacitance as 10 femtofarad, and this has to be varied. For example, if you look into a non-linear delay models or NLDM, the output capacitances is varied in a range. So that's what we have to do. So let's say for a simple setup, we are going to look into a fixed capacitance and figure out what is the characterization behavior looks like. And then finally we have the 8th step, which is you need to provide the necessary simulation command. So over here we are doing a transient simulation, so we give .tran. If you do a DC simulation, we have to give .dc and so on. So we have talked a lot about this thing also in the circuit design and SPICE simulation course. You might want to have a look into that. So these are the 8 different unique steps that we have for the characterization flow. Next step is to feed in all these inputs from 1 to 8 in a form of a configuration file to the characterization software called as Guna. Okay, I will talk a lot about Guna as we follow in this particular course, and this thing, the software will generate timing, noise and power models. Okay, now coming back to the information that you get out of the Guna software, the timing, noise, power .libs brings us to a very important classification of .libs. The one is the or a classification of the characterization type. We have the timing characterization, we have the power characterization, and we have the noise characterization. So what we'll do is we'll stop at this point, and we'll talk about timing characterization from the next video. Thank you. Hello everyone, let's begin with the timing characterization, and this is the video onwards where we are trying to understand the various syntax and semantics of a timing.lib, a power.lib and a noise.lib. So we are going to understand these concepts behind the syntax and also the syntax and what does the syntax itself represents. And these syntax are really very important to understand the Guna software, the characterization software, because the software works on variables, and these are the variables that are being available with us in order to feed into the software. So let's try to understand those variables as of now. So to begin with, we are going to look into the SPICE or the characterization setup that we had explained in the last video. You have this inverters connected back to back, you have the power sources, you have the stimulus that is being applied over here, you plot waveforms over here, you plot waveforms over here. So this brings us to a very important point of understanding the different threshold points of a waveform itself, and that's what we call it as timing threshold definitions. Okay, so these are the points, or these are the inputs, or these are the variables that are related to any waveform that you see, that you will be seeing henceforth. And so let's begin with the definition. So first of all, you have the slew low rise threshold. So what I have done is I have taken the waveforms from the output of the first inverter, which has been given as an input to the second inverter. So this is your input, and this is the waveform from the output of the buffer. So for example, I had shown 2 inverters back to back. So this is the output, or this is the input to the second inverter. This is the output from the second inverter. So that's why it's called inverter out. So this is the output of the first inverter, which goes as an input to the second inverter, and we have written buffer out, which says this is the output of the buffer. Okay, so we'll use these waveforms to basically define or to understand the different syntax that are associated with these variables that you see on the screen. So the first of all is slew low rise threshold. So whenever we say low, whatever we say low over here, those depicts the values that are close to your zero power supply. So for example, when we say slew low rise threshold, it basically says if you want to calculate the slope of this particular waveform or the slew of this particular waveform, you need to have 2 different points. Those points could be this point and this point, or those points could be this point and this point, or those could be this one and somewhere over here. But you need to define this value. So whenever we say slew low, it basically defines the point towards the lower side of your power supply, which is 0 volts. And the typical value of slew low rise threshold is about 20%. It could be 30% as well. We'll get back to that in a moment from now. Okay, so let's begin with let's assume that the slew low rise threshold is 20%, and we put a value over here. But that's not enough to calculate the slew. We need the slew high rise threshold as well. So slew high rise threshold comes somewhere over here. Again, we have, for the sake of simplicity, we have kept it 20%. So whenever you want to calculate the slew of this waveform, you just take the point from 20%. You just take the point at you just take the point 20% from the bottom power supply. You take a 20% point from the top power supply, and just identify the time difference between this, and that's where you calculate the slew. I'll get back to calculation of this slew just after this particular video. Okay, so that's basically slew low threshold and slew high threshold, and this were all for the rising waveform. Similar definitions also applied for the falling waveform as well. So in this case, the slew low fall threshold lies somewhere over here, and the slew high fall threshold lies somewhere over here. So what are the applications of identifying these thresholds and these values? So I'll get back to that when we go to the propagation delay concept. So let's try to understand the definitions first of all. Okay, so you need these values to calculate the slews of the waveform. That was one thing. And next, let us try to look into the other definitions. For example, you have the in rise, in fall, out rise, and out fall. So these are all related to your input waveforms. Let's try to look into those as well. So for example, this is the input stimulus that we have applied. So remember, in the last video we were doing a transient analysis. So those transient analysis we have specified some input waveforms. So let's say this was the input waveform, and this was the output of the first of the buffer. So we have taken the complete buffer as basically two inverters connected back to back. We have taken the complete waveform, and we have given this stimulus as the input to the waveform, as the input to the circuit, and we have taken the output from the buffer. And this is how it looks like. So this is your input waveform, which is an ideal waveform, because this is the thing that we are applying, and this is the output of the buffer. So now let's look into the other definitions. In rise threshold. So similarly, what you had for the thresholds for the slew, you also have thresholds for your delays as well. So for example, if you want to calculate the delay of this particular cell, of that particular inverter, you need some points to calculate the delay. Those points could be this point, or this and this, or this and this. This becomes the best point that is being defined in order to calculate the delay, and the points which are being taken across this waveform or across this waveform they are also possible. But in this case, we'll take the 50% point of this particular slew waveform. So 50% lies somewhere over here. That's what you call as the in rise threshold. So you need this point and one point on the output waveform in order to calculate the delay. So this is the in rise threshold, which is the typical value of the in rise threshold is 50%, and it says input. So this is the input waveform. This is the rise. So this is a rising waveform. Okay, and similarly, you have the out rise threshold also as 50%. Out rise threshold is basically the output waveform. Whichever is the output waveform, the rising point or the output rising waveform, the point at which you can calculate the delay, that point is basically out rise threshold. So now if you want to calculate the delay between the cell, you just need to take this time period. You need to take this time period, and that's it. You will get your delay. Okay, so the software uses this thing to calculate the delay. So that was about the in rise, and similarly you will have something for the fall as well. So if you apply a fall waveform, let's say this thing, if you give a fall waveform to your input, you get the buffer output will be a fall waveform, and the definitions remains the same, the wordings remains the same, only the things are now getting applied for a fall waveform. So out in fall threshold will be something over here, which is 50%. The typical value is 50%, and out fall threshold will also be 50%. If you want to find out the fall delay, so a buffer has got two kinds of delay. Any one input gate, a single input gate has got two kinds of delay. One is the rise delay and one is the fall delay. So this is, in order to calculate the fall delay, you just need to take the 50% value from this point. You need to take the 50% value from this point, take the time points from this one, and take a difference of it. So I will talk more about the propagation delay when we reach there. So these were all the definitions of your of the timing threshold definitions. Based on this thing, based on these 8 values, we are going to calculate the further values. For example, we are going to use these terminologies to calculate the slews, to calculate the propagation delay, to calculate the current, and a lot of things. So we are going to use all of them as we move ahead. So let's try to stop at this point, and let's try to begin with the next timing characterization parameter, which is propagation delay. So let's talk about propagation delay from the next video. Thank you. Hello everyone, let's continue with the next timing characterization topic, which is propagation delay. So propagation delay sounds to be very easy, but if not taken care, it might lead to some unexpected results. So let me show you what I was just talking about. So let's say you have the same characterization setup as we have shown in the past video. You have the input waveform, you have the output waveform, and we also have defined the characteristics of the waveform or the threshold points of the waveform. With that, on that basis, let's say you have this in rise threshold, in fall, out rise, and out fall. Then if you want to calculate the delay of anything, you just need to subtract out minus in. That's the standard definition. So for example, let me write down the definition over here. You just need to find out the time at the out threshold. You just need to find out the time at the in threshold and subtract out minus in. And why out minus in? Because out comes later and in comes early. So out minus in should give you the exact delay of, let's say, this particular inverter or this complete buffer. Now let us try to put some valid values over here. So let's say we'll take a typical value of 50%, which is being followed across the industries. It might vary across 50%, but let's say we'll take a typical value of 50% as of now. So with this 50% in mind and with this thing definition in mind, this is a very important definition because this is the one that leads to unexpected results, and I'll show you how. So this definition and this 50%, let's take a waveform, let's take a sample waveform and see how can you apply all this in that particular waveform. So let's say you have this as your input waveform. If you have this as our output waveform, this is the same waveform that we have taken from the output of this second inverter. Okay, so if you choose the threshold points as 50%, so let's say this point of 50% lies somewhere over here, and the time point at the 50% is 3.207 nanosecond, and the time point at the outfall threshold is about 3.230 nanosecond. If you want to calculate the delay, it's pretty simple. It's just 3 out minus in. So out minus in is 3.23 minus 3.07. So 3.207, that comes to about 23 picosecond. All well, all good. So but the next problem is if there is a movement of the thresholds over here, it creates a problem over here. So for example, in this case, the in rise threshold was kept as 50%, outfall threshold was kept as 50%. But by any chance, if the threshold points moves somewhere to the top over here, the threshold points have changed, your time in rise, the in rise will be 3.263 nanosecond, which is this point if you see on the screen, which lies somewhere over here. Your time outfall threshold lies over here, which is 3.221 nanosecond. Typically what you see is your output comes before the input, and that's why you see a negative delay of negative 42 picosecond. And that's not correct, because negative delay are not expected. You need a positive delay. So the reasons behind having this kind of negative delay is poor choice of your threshold point. So choosing the threshold points is really very important, and this is a very common problem that we see when we write out the dot lib where we see a negative delay. So these are really very important thing to look about in the characterization tool. So this is correct choice of threshold is really very important. Again, there is another example where we choose the correct threshold, but still you can get a negative delay, and that could be if you have a waveform something like this. So if you see this particular waveform is your input waveform, from the slew of the input waveform, you can figure out that the wire delays are pretty high. Okay, this could be one of the reasons where your layout, the two inverters are placed very apart. You remember that we have seen a layout over here. So the two inverters are very far apart, and you have a huge wire between two inverters, and that might lead to the output of the first inverter to give such huge slew. Okay, so even with this particular kind of waveform, even with the proper choice of thresholds, let's say you have this particular, we'll try to zoom into this area and see what are the values at the in threshold and the out threshold. Let us try to zoom into this area. Okay, so if you deeply look into that area, your in rise threshold comes to about, which is 50%. 50% is nothing but 0.9, 1.8. If you take the 50% of 1.8 volts, it's 0.9. So if you look into the in rise threshold, which comes somewhere over here, it will fall about 4.215 nanosecond. Your outfall threshold will fall about 4.207 nanosecond, which is over here. Again, your output comes before input, that will give you a negative delay of 8 picosecond, which is not expected. So again, if you have taken the right thresholds, but if your circuit is not designed properly, if it has got huge wire delays, it might lead to negative delays. So these two things needs to be taken care of while choosing the thresholds and while designing the circuit. So circuit design step is a really very important step to if you try to figure out if you try to conclude from this video. Okay, next we are looking into the next topic, which is timing characterization for transition time. So transition time is pretty easy to identify, because you have the values of slew low rise and slew high rise. So for a rise waveform, you just need to subtract the high minus low, and that will give you a slew. That will give you the slew of a waveform. Okay, similarly for the falling waveform, you just need to subtract the high minus low for the fall, and you will get the slew waveform. Okay, so let's try to take some values or take some typical values for the slew rise and slew fall. So for example, we have the values that we take is 20% generally. It could be 30%, and also it could also be 30%. So slew low rise threshold is 20%, and slew low fall threshold is 20%, and we'll take a value of 80%, let's say, for the rise value. So when you say 20%, it's 20% of VDD, 80% of VDD. So with this definitions or with this timing threshold in mind, let's try to identify some transition time over here, the input transition time or the rise transition time and the fall transition time. Okay, in case of a setup, in case of a circuit, there is no input or output, there is a rise transition, there is fall transition, and there is rise delay and there is fall delay. So let's try to look into one of them. So let's say you have this definition set aside, and that 80% of your VDD is 1.44 volts. The 20% of your VDD is 0.36 volts, and with this now you have got all your threshold points. So this is your slew low threshold, this is your slew high threshold for the rising waveform. Okay, this is your slew low threshold, slew high threshold for your falling waveform. Now if you want to find the rise transition, just subtract this point minus this point. Let's see what value do we get. So if you have this point, the input slew comes to about 26 picosecond, which is from this point to this point, you just subtract it. Your output slew comes to about 54 picosecond, which is again high minus low. It has always to be high minus low. It can't be the other way around. So that brings us to an end of the timing characterization for the transition time. Let's look into the next one, and since I'm running a bit late out of time, let's try to look into the output current waveform. This is again very important timing characterization thing that we need to look into: output current waveform and the output voltage waveform. And these are the waveforms that leads us to the CCS timing.libs and ECSM timing.libs. So let's talk more about output current waveform from the next video. Thank you.